All right. Good morning. So, welcome to the workshop. So, this workshop is in general about spintronics and magnetism, and specifically focusing on altermagnetism. We have, all the leading experts. They'll talk about the theory and also the experimental progress of this new emerging concept. So the talk is in general 40 minutes, but something like 30 minutes talk plus 10 minutes Q&A, but it's flexible. So we have four talks in the morning and 3 talks in the afternoon. Our first speaker would be Professor Igor Marzin from George Mason University, and he kindly agreed to give an introduction to the entire topic. Yeah, please, Igor.
Okay. Hi, everybody. I'm a bit embarrassed to give a simple introduction talk, but that's because Su Yang explicitly asked for that. I'm afraid that most of the thing I'm going to talk about is known to all or most of you, but well, it is what it is. So I'm going to speak about 3 things. First, about why do I think, among others, that this phenomenon is interesting and different enough to deserve another name. And basically, what do we decide to call altermagnetism, and why does it have both ferromagnetic and anti-ferromagnetic properties, and sometimes even more than that? And then there's a little bit of controversy about how we should rigorously define things. Then I will talk about the question very often asked by my experimental friends: what are the symmetry rules that control antimagnetism? It's actually, again, extremely simple, if not primitive. And I will tell you about that, and I will also introduce a very simple tool regarding just doing that automatically. And finally, I will discuss a little bit of the thing how we can use these symmetry rules to functionalize, just take regular antiferromagnet and make it altermagnet. And finally, yeah, that will be my example. And finally, by the way, on my screen, I have this floating bar at the bottom. Is it covering my slide on the bottom left?
No, it's good.
No, everything is fine. Okay. So that's, if time allows, I will discuss a little bit of a phenomenon that is formally different, but it's extremely close, both in properties and in many ways. It's not just an independent thing, but I would call a sibling of altermagnetism, and that's something that I called Latinger compensated ferromagnetism. So, what's altermagnetism? Those who were in this business from the very beginning, which was very recently, know that it somehow came into limelight. Well, maybe not very very big, very bright spotlight, but essentially started to be discussed about 4, maybe 5 years ago. And at that time, at least 5 groups independently stumbled upon this phenomenon, even though it's extremely simple and very well could have been discovered or paid attention to 20, 40, 50 years ago. And different groups call it different names. Most of them names not very informative. I started calling that anti-Kramer's anti-ferromagnet, which is a bit clumsy, that Lieber and his collaborator, Crystal Hall, anti-ferromagnet, which is simply wrong. Then the Alex Zunger group, staggered spin split anti-ferromagnet, which is correct, but not very catchy. Then the Chinese group invented a name which I honestly don't even understand, C-pair spin valleys locking. And then finally, Thomas Jungwirth came with a name which is both appropriate and catchy, and it sort of gets stuck in the community, altermagnetism. So to begin with, what is ferromagnetism? ferromagnetism from symmetry point of view is a material where time reversal, which is equivalent to spin flip, leads to a crystal which is symmetrically different. There's no symmetry operation which can map the left panel onto the right panel. Now, because these two things are different, that means that the band structure in two spin channels is generically different, like in two different materials. So the bands are not spin degenerate. There's no reason to have the same energy for two different spin and the same momentum, except that maybe accidental crossings. There is, of course, net magnetization. There is anomalous Hall effect. There are magneto-optical effect as well, which is just nothing but finite frequency generalization of the anomalous Hall effect. So all these things well known. And in fact, interestingly, such things as anomalous Hall effect and very strongly magneto-optical Kerr effect had been routinely used in the experiment as determined whether material is ferromagnetic or not. As we will see, it's not even works this way always. So now what is conventional antiferromagnet? Conventional antiferromagnet means that specifically, this example is of iron rhodium in its high temperature phase. It's interesting material which has both ferro and antiferro phase, depending on the temperature. Basically, spin flip is equivalent to spatial shift, spatial translation. That is to say that it's essentially the same material when you flip spin. And because obviously the spatial translation doesn't change electronic structure in the momentum space, you can say that all bands should be spin degenerate everywhere. But obviously there is no net magnetization and there is no anomalous Hall effect and no magneto-optical effects. Now these are, you also can call them, if you want, nail ferromagnet, because those were antiferromagnets that were initially introduced by Nail, and surprisingly, it may be some of truly highbrow theorists never even thought about any other type of antiferromagnet, although experimentalists know very well that there is also, and has been knowing for a long time, that there is something that is called zone center or Q0 antiferromagnetism, and that's a good example. Consider iron oxide in its high pressure phase, which is also called inverse nickel arsenide structure. It's a hexagonal structure where non-magnetic atoms form just simple hexagonal lattice, and magnetic atoms are these two. So there are two atoms, two iron atoms in this case, in the unit cell. And if you flip spins, you can clearly see that this is that the structure is different, but it's symmetry equivalent. There is a symmetry operation because both these iron atoms belong to the same, what we call in crystallography, Wyckoff orbit. That means that there is asymmetry operation that maps one onto the other. In this particular case, it's not, of course, translation, it's actually inversion. Here I illustrate it very clearly. This is inversion center, this gray ball, and you can clearly see that inversion operation maps all green atoms upon themselves, and at the same time maps one iron onto the other iron. Now, the interesting part of the inversion operation is that in non-relativistic case, whether actually this inversion symmetry, that's true even in the relativistic case, that flipping spin and simultaneously flipping electron moment does not change electronic structure. So this is the general rule applicable to any material. Now, if the same symmetry operation inversion in this case also is equivalent to spin flip, time reversal, that means that all that these two equality hold independently. That means that basically for given momentum k, spin up and spin down states are degenerate. So we are back in the realm of conventional antiferromagnetism or ramification. But now let's say, consider iron oxide in the actual nickel arsenide structure. And there are magnets that crystallize in this structure, like chromium antimonide or manganese telluride. Now, see, it's exactly the same structure, but now my non-magnetic atoms are those atoms which are related by inversion symmetry. But inversion center here, which is right in between, it actually maps one iron spin upon itself. There is a symmetry operation, definitely, which maps one sublattice onto the other, but it's not shifting. You know, if I try to shift, then, of course, my green atoms end in the wrong positions. And the midpoint is not inversion symmetry. As you can clearly see, again, it's the same sketch. It's a mirror. It's a mirror, very simple mirror, but there are also other symmetry operations like glides here or screw, but simple mirror does it. But mirror and actually no other operations besides inversion has this property that it conserves the electron energy. So that means that the second part of this equation doesn't hold. So the bands can have non-zero spin splitting, and we know that in nature, if something is allowed by symmetry, it will have it. And let me illustrate on a very simple toy model how that can work. Let's say this is the simple construction which is recognizable as two-dimensional perovskite plane. So this is blue ball is a metal, and the gray thing is a ligand like oxygen, for instance. There is one formal unit per cell, so it's one metal atom per cell. And if we make it if you make this structure ferromagnetic, the unit cell remains as it is, and there are two, generally speaking, unrelated bands. Now, suppose we make an antiferromagnet. In this structure, the only way to make antiferromagnet is to double the unit cell. Now, my unit cell is like this, rotated by 90 degrees, square root 2 by square root 2. I have 2 atoms per cell, and inversion center sits between these atoms, so inversion symmetry does map one spin onto the other, so my band structure will be spin degenerate. But now let's say something that often is called Kugel-Chomsky orbital ordering, and unfortunately, Daniel Chomsky very sadly passed away recently, but even so that it goes back to 1960s. There are good physical reasons for similar such perovskite structure to get distortion which corresponds to orbital ordering on metal atom, and which can be easily seen in the ligand environment. So you can see that this is the same octahedron, well, in this case, rhombus, the same diamond around each metal line, but they are rotating, they are staggered. So now, even without magnetism, my unit cell is doubled, and it has two metal atoms. And there is symmetry operation. It's actually it's a rotation axis here, but it's not inversion symmetry. So there is no inversion symmetry operation which maps one spin onto the other. And you can clearly see in this toy model how does it work. Let's say we start from this red atom in lower left corner. And let's say we proceed along the x-axis. So what we go first along the long axis, then short axis, then long axis, and so on. If we go in the other direction, that will be a different dispersion because we start from short and then go long. But now, if we start from an atom with an opposite spin, you can see that if we go up vertically from the blue ball, it's exactly the same as going horizontally, starting from the red ball. So that without any calculations, you can see that it must result in the band structure like this, where you go along X, you have spin splitting, but when you go along Y, you have the opposite spin splitting. So that's arguably the simplest possible model for altermagnetism. Now, that can usually be seen, very easily can be seen in band structure. So this is the left side is for chromium antimonide, the right for isostructural manganese telluride. On the left, it's from paper by Lieber and other. This material is interesting by the fact that the spin splitting is exceptionally large, but it's not that surprising because as opposed, for instance, for things like Rashba splitting or something, microscopic parameter that determines the amplitude of the splitting, generally speaking, in Hund rules coupling. It can be attenuated by other factors, but the scale is set by Hund rules coupling, like in ferromagnets. And Hund rules coupling, the scale of Hund rules coupling in 3D metals is like 1 electron volt, in 4D 0.6, and in 5D 0.4, 0.3, but it's a large number. The other thing is, so this band structure is, unfortunately, I had to cut the bottom, that was long thing, but it's basically going to 2 different points. One is starting from gamma point, and gamma point, of course, is always degenerate. Then you go along 2 different directions, the hexagonal unit cell, different but not opposite. If they were opposite, then the spin splitting will be the same. This manganese telluride, it's as opposed to chromium antimony, it's formally semiconductor, although an experiment is always comes self-doped. And here I just, for illustrated purposes, I combined Fermi sources with small hole doping and small electron doping. You can very clearly observe that how the symmetry of this object is going. This is each individual spin follows trigonal symmetry, so 3 axes. Taken together, if you forget about the sign of the spin splitting, it follows 6-fold symmetry. And you can see how these things alternate in the 3-dimensional space. Very interestingly, there is a nodal plane here, and probably Libor will be talking more about symmetry classification of different altermagnets. And in this particular case, it's imposed by symmetry. There are other similar hexagonal cases when it's not the case, and so on. So now, with all this knowledge, let's ask us this question. Do we really need to amend our classification scheme, if we do have a classification scheme at all for magnetic materials? And I cannot stand temptation, quote from one of my favorite authors, Jorge Luis Borges. He had a sort of somewhat surrealistic essay or novella called Celestial Emporium of Benevolent Knowledge. The part of the plot is that there is a text discovered from written in ancient Chinese, which is called an encyclopedia of benevolent knowledge. And in some parts of the encyclopedia, there is classification of all animals. So it's so funny that I will give you time to read that through. And paradoxically enough, it's very often, it's exaggerated principle how people classify different things in physics. I will not dwell too much on that, but you can easily find examples when it really goes like this. And of course, whatever classification whatever animals one is studying at this moment of time, they always belong to category 6, fabulous ones. So jokes aside, let me give you my personal attempt of classifying magnetic materials. So the non-magnetic materials is another animal. Magnetic materials have non-zero magnetic density, which may or may not be collinear and may or may not integrate to 0. So there is a whole world of non-collinear materials. I know that there are some people in our community which want to somehow introduce altermagnetism as a concept crossing from collinear to non-collinear. Other people, including, for instance, Libor, who's present here, and myself, and other colleagues of ours and mine, we believe that it's not constructive, that altermagnetism is a concept which works best in collinear system, and it's going a little bit jumping ahead. It's somewhat psychological. We were older generation. We grew up with understanding that, for instance, if you work with anomalous Hall effect, that collinear antiferromagnets do not have anomalous Hall effect. Turned out not to be true, and we also grew up with understanding that non-collinear antiferromagnets, generally speaking, have anomalous Hall effect, although there might be exceptional cases. So it turns out that this intuition is not accurate in both cases. There are non-collinear magnets which don't have anomalous Hall effect by symmetry, although they are maybe less common. And there are also exceptions from the rule that collinear antiferromagnets do not have anomalous Hall effects, and those are altermagnets. So let me concentrate on collinear magnets. Again, we can think about incommensurate, which would be spin density wave, or experimentalists often partition them into spin density wave and spin spiral. For theorists, it's the same thing. And commensurate. And commensurate, again, the symmetry is the strongest instrument that we have in our toolbox, and they can be compensated by crystal symmetry or not compensated by crystal symmetry. They can be ferro or ferromagnet. From theory point of view, it's the same thing. And ferromagnets can be uncompensated, which is literally exactly the same as ferromagnetism. They can be compensated by virtue of Luttinger theory, the theorem, which I will explain later. And also, when you go back to crystal symmetry compensated, there are sort of this is preserving momentum space symmetry. And that basically means that crystal symmetry that is responsible for this compensation is either spatial translation or inversion. And those which are not preserving, and these are we call altermagnets. So this is, I was chastised by Jairo Sinova that this is an incomplete list, but I couldn't really fit more into one slide and make it still readable. I think it still drives the point through. This is the list of various properties that we consider in different applications, different theoretical constructs regarding. Is there a question in the audience? Interrupt me because I don't see if somebody raises a hand. If you want to ask a question, just interrupt me. Simply unmute yourself and interrupt. Okay. All right. So, of course, the defining problem is net magnetization. And yes, net magnetization in ferromagnets can be non-zero, or it can be zero in ferrimagnets, and it's zero in antiferromagnet altermagnet. But if you go down the list, funny enough, it turns out that altermagnets share many more properties with ferromagnets than with antiferromagnets. They have no Kramer degeneracy, they have anomalous Hall effect, magneto-optics that can be used for spin current splitting. They can suppress Andreev reflection, although by more strict conditions than ferromagnet, although in diffuse regime they don't. They cannot support single superconductivity, while antiferromagnet can. They cannot support unitary, even unitary triplet. They cannot support, which ferromagnets cannot either. And they, as opposed to, in fact, as opposed to ferromagnet, they can support average unitary triplet superconductivity, something very interesting, which we are not going to discuss here. They can have tunnel momentum resistance, and as Jairo justly points out, numerous other properties. So this is really something that we. Why am I? Oh, okay, right.
Sure,
So
I have a question.
Yes.
So for the anomalous Hall, is it that the altermagnet can have anomalous Hall, or altermagnet must have anomalous Hall?
Yes to the former, no to the latter. It can have anomalous Hall effect, but it must not have anomalous Hall effect. There is an difference which is not reflected in this table, that basically ferromagnet, if I understand correctly, if you have a ferromagnet, then you will have, no matter in what direction your spin point, there will be always at least one geometry where there is non-zero anomalous Hall effect.
Okay.
In altermagnet, that's not necessarily the case. For instance, one annoying issue with chromium antimony, which is otherwise is high nail temperature, very good metal material, is that the nail vector, that is the direction of chromium spins, is along 0, 0, 1 direction. And it turns out that for this direction, no anomalous Hall is allowed in any geometry. In fact, the code that Andrei Smoleny code that I will present to you quickly later, and which will also be presented in a tutorial on altermagnetism at the next March meeting, it can tell you simply based on C files and the magnetic pattern, whether this pattern is altermagnetic, and also whether it has anomalous Hall effect, and if it does, in what geometry.
Okay, sounds good. Yeah, thanks.
Okay, all right. So let me just a bit of advertisement for which probably, I don't know if it will be or not, but probably will be covered in Libor Schmeichel talk, just because I sort of like his theory, even though I have not contributed anything at all, not even on discussion level. It's interesting to go back into 1892. In 1892, the 20 years long collaboration between Fedorov and Schoenflies, who never met in person. One was living in Russia, I think in Kazan, and the other in Germany, I think in Dresden. I may be wrong on both locations. And they were sending each other letter, which whatever these horses were taking them over for 2 months. And then by 1892, they figured out all space groups allowed in nature, which to me is an amazing feat. But for us, what is it? So this is the purely chart that doesn't include any magnetism. So the object that they were considering is an atom, which they could be different atoms, different ions, but they didn't consider spin, and that already results in nearly 200, more than 200 space groups. Now, about 60 years later, Shubnikov, another Russian crystallographer, in 1953 introduced magnetic group theory. And that was enormously more complicated for the reason that spin, generally speaking, is not the same object as charge. It's a pseudo vector, and that means that if you consider, for instance, a symmetry element, let's say mirror, then the way how spin responds to these symmetry operations depends on how the spin is directed. If it's parallel to the mirror plane, you can see that very easily, because spin has the same property as a circular current loop. So you can see that this spin flips direction, or if it's perpendicular, it does not. And that results in enormous complications. And basically, spin group, the magnetic group depends on what is the, even for collinear materials, what is the direction of the spin, and there are thousands of them now. So we really, we cannot live with non-magnetic group theory if we want to classify altermagnets, but magnetic group theory is just too much, and it's unnecessary introduce distinctions, and I will show on the next slide, between things that from altermagnetism point of view should be considered essentially the same. So for that reason, Libor Schmeichel, and many people did that similar things before. The idea is that you should, specifically non-relativistic, and why am I saying non-relativistic? Because the only way how spin direction can manifest itself in crystallography is through spin orbit coupling. Otherwise, spin space and real space are not coupled. So it's might be interesting to introduce object system which consists of two color objects, which can we call spin up and spin down, but direction doesn't matter. I like the version that Libor developed, incidentally, also nearly 60 years after Shubnikov, which is very well tailored for classifying altermagnets. So let me give you an example on these structures we already considered: manganese telluride and chromium antimony. One of the two most popular crystallographic motifs for altermagnetism. The other one are rutiles, which is unfortunate because rutiles, I suppose manganese telluride is self-doped semiconductor, chromium antimony is a metal. So many things can be studied there. So far, all known magnetic altermagnetic rutiles are strong Mott-Hubbard insulator, like manganese difluoride. There was one promising candidate, ruthenium-02, which turned out to be just imposter. It's not magnetic. Later today, Roser Valenci will talk about that. But anyway, rutile is a very neat structure, but we want to find better examples. And this structure is works better. In fact, there are direct measurements of band structure on both of them, which confirm the theory. So let's look at the non-magnetic space group. Is group called 194. It's has six-fold symmetry. This is the standard crystallographic notation for this group. Now we introduce magnetism in Shubnikov sense, so we include spin-orbit coupling. Then if my magnetic moments are along 0, 0, 1, then the six-fold symmetry remains. There is particular magnetic group. If we position our moments along X direction, that means along the manganese-manganese bond, metal-metal bond, it's now orthorhombic, body center orthorhombic material. And if I position them along Y, perpendicular to the bond, even though it looks very similar, it's actually a different magnetic group. Now, in Libor's classification, it belongs to spin group number 24, and they're all three are the same. Now, all these three guys are altermagnetic, but not all of them have anomalous magnetotransport response. In fact, only the last one on the right does. It has anomalous Hall effect and obviously magneto-optical Kerr effect, but not the other two. So now going to the second part, I'm already 30 minutes to my talk, so I maybe need to go faster. So there are, it's all very simple. You just can formulate it in a sort of algorithmic way. And let me just skip this slide. There is a very simple algorithmic recipes, how you can proceed in the simplest possible way to check. And then Andrei Smolenuk from Vienna, with my help and help of Libor, wrote a very cute code, which you can find on GitHub and also described in this journal, which I never heard about, but Andrei said that's the right place for a code. It can test C files, WASP phosphor files, and can also test magnetic structure for selection rules for anomalous response. So as I say, there's an email you can write to the guy. It's also on archive and will be full tutorials will be presented the Sunday before the March meeting. Now, next part is using this understanding of how symmetry makes or does not make material altermagnetic. Let's think whether we can actually take an existing antiferromagnetic material and, oh, sorry, that's the type, converting into altermagnet, not AF to AF. This would be too simple. So yeah, this is a very known crystallographic motif. There are numerous materials with this. They're all van der Waals exfoliable. So this is one example, manganese PS3. So you can see that there are two manganese atoms here, magenta and blue, and there is an inversion symmetry between them. Now, importantly, there are other symmetry operations that map one onto the other, but among them, there is also inversion. That's enough to make it normal spin degenerate antiferromagnet. And you can do calculation. The calculation, of course, confirms that because symmetry never lies. So now I will give you three ways in which we can actually slightly modify this material and make it immediately altermagnetic. So in this case, I make it genus. The genus means that my bottom layer, you remember this here, I was showing that this is a bottom layer and top layer. Now, this material exists in this mixed phase as well, but so far experimentally, the selenium and silver are always distributed uniformly. In principle, for other chalcogenides, people can make genus monolayer, which means that material, the chalcogen below the manganese layer is predominantly sulfur and above predominantly selenium. Then this point is not inversion symmetry anymore. There are still, in fact, there is still mirror symmetry, which convert them. So it's, of course, it's fully compensated by symmetry, but now it becomes altermagnetic, and you can clearly see how you can remember that was my Fermi surface here, and now how this Fermi surface becomes when I introduce this genusization. You immediately see that there are some other aspects here, very interestingly, how that it behaves in terms of rotational symmetry. Because you may remember that for another hexagonal material, we had by symmetry a nodal plane at kz equals 0. So you would think that it's not possible, but it actually is possible. Another example is is gating, and 1 volt per angstrom is a large but not impossibly large gating. Then again, you get something similar to that. And the last one, you can do bilayer epitaxial contacting that with I selected molybdenum ditelluride here because they have essentially exactly the same exact matching of the lattice constant, and then you get a really strong effect, dramatically strong effect. It becomes altermagnetic in also with there's some charge transfer in a very interesting way. And finally, in the last 2-3 minutes, lattice compensation versus symmetry compensation. So let's take standard metal. This is spin polarized iron in the BCC ferrite phase. There are 2 different densities of states here for spin up and spin down. They have nothing to do with each other. There's a net number of spins with spin up and spin down is not the same, and actually can be any number. Doesn't have to be integer. Or compare that with another material, which is iron 304, this classical magnet hematites. It is actually what we called half metal. So there is a gap in one spin channel, and because of that, you have density of state in up channel has to integrate to integer number. And then again, by charge compensation, even though the Fermi level and down band is in the metal, is metallic, it still has to encompass an integer number of spins. So that means now that the net magnetization doesn't have to be 0, but it has to be integer. That's what I call this Luttinger compensation. That is to say that if chemically these guys want to be close, small magnetization, they cannot have small magnetization. They can have, they would have 0. In this case, they're happy having finite magnetization. There are other examples which I will. So this is just a few examples of this Luttinger compensated ferromagnet. This is europium arsenide. This is monolayer of manganese fluoride. But I want to squeeze to this. That's, you remember, that's a relatively old paper, and it's by far not the first. These materials had been considered before, but they were sort of miscalled. It's misnomers. They were, people used to call them. This paper actually does it correctly, but other paper call it antiferromagnetic half metal, which is wrong because it's not antiferromagnetic, it's compensated ferromagnetic. So this is an interesting material. It has 2 different types of manganese, and somehow they are so chemically located, they want to have a small magnetic moment, and that means that they would have exactly 0. And in such a way that one manganese has exactly twice larger moment than the other. So that, essentially from most, not 100%, but 90% of interesting properties of altermagnets remain in this Luttinger compensated ferromagnet. So it's a perfectly legitimate route to explore all sorts of spintronic applications and everything. And final slide. So why did I call them siblings? Even though not only because they have similar properties, and as I say, sharing most of the feature. Let me give you an interesting example. Take manganese difluoride. It's which was before I was showing a single layer, and this material doesn't exist in single layer, so it was just a sort of a theoretical exercise. But you can apply strain to this material. So if it's unstrained, then you have manganese, which has double degenerate Wyckoff position. When it becomes magnetic, it becomes altermagnetic. That's a known fact. Now I apply 100 strain. 100 strain changes this to an orthorhombic structure, but the symmetry operation, this is this the screw, 4-fold screw axis in this case, which maps one manganese onto the other, remains. So they are still the same, and also 2A incidentally. But if you apply 110 strain, even infinitesimally small, then this symmetry is destroyed. And now I have CMMM positions different from the one before, although it's also orthorhombic. Now I have 2 different manganese. One is 2A and another is 2C. Don't pay attention, the number didn't change. It's just because crystallographer always use conventional unit cell, which is twice primitive. There is one manganese A and one manganese C. And now these things immediately becomes ferrimagnetic. And you can see that here I plot, for instance, this, you see gamma point. In gamma point, the bands are degenerate by symmetry in ultramagnet, but not in compensated ferrimagnet. And this is this splitting plotted as a function of 110 distortion. You see it's perfectly linear, and it's actually not that small for small. So that means that these things are really genetically connected. In fact, if it hadn't been a metal, there would be also net magnetic moment, also linear in this distortion. So I think I will end at this point and we'll take questions.
Okay, thank you so much, Lieber. Yeah,
Thanks a lot. I'm looking forward for the next talks.
thank you. Okay, so next we have Professor Daniel Rolfe from Cornell University, and he's going to tell us about van der Waals magnets and antiferromagnets interacting with electron spin.
Yeah, so hi, everybody. When Su Yang first contacted me and invited me to participate in a workshop on altermagnets, I said, that's really neat. I appreciate it. But I'm not sure it's a good idea because no one in my group has worked on anything related to altermagnets for 3 years or so. After some back and forth, we agreed that I would talk about my most recent work. But if anybody is interested in talking about our past work on spin orbit or spin current-induced torques from ruthenium oxide and things like that, happy to do that either during the question session or offline. But that's not what I prepared to talk about today. So I'll actually talk about 2 stories that I hope will be of interest. One has to do with creating topological states by a proximity interaction between a topological insulator and an adjacent magnet. And what we've done there that's different from previous work is we use mechanical stacking, the techniques people use for 2D materials to create those interfaces rather than deposition techniques. And it turns out that creates a dramatic difference in the strength of exchange interaction between the magnet and the topological surface state. We can see quantized anomalous Hall effects above 10 Kelvin in these materials, which is about a factor of 100 more higher temperature than what's been seen previously with the deposited structures. So I'll tell one story about where that research stands. And then I'll also talk briefly about a second project involving antiferromagnets, where we've been trying to develop techniques both to detect the high frequency dynamics of antiferromagnets directly and to begin to manipulate those dynamics electrically in a scaled structure, a micron scale device. So just some background about what happens when you combine a magnet with a topological insulator. If you have a magnet with out-of-plane magnetization, that can produce an exchange gap in the topological surface state. And if you can position the Fermi level within that exchange gap, the Berry curvature from that exchange gap gives you a large Hall effect. And it's an anomalous Hall effect. If you just gap one surface of the topological surface state, just have a magnet on one side rather than both, you actually get a Hall conductivity of E squared over 2H. So half the usual value for a quantum Hall effect. And this is called a parity anomaly state. It's a bit unusual in terms of quantized Hall effects in that it doesn't have 0 longitudinal conductivity because the bottom surface of the topological insulator isn't gapped. You still have non-zero longitudinal conductivity there. So these are the sort of structures our group has been making so far. You can also go on and try to gap both surfaces of the topological surface state. And all 3 of these states have been made with magnetically doped topological insulators. But with magnets on both top and bottom and with parallel magnetizations, the Hall conductivities on the 2 surfaces add to give you an integer quantum Hall effect. And you do get 0 longitudinal resistance in this case, and nice dissipationless chiral edge states along the edges. So all the properties you would expect from a quantum Hall effect, but it's 0 applied magnetic field if the magnet has a good coercive fields. You can also arrange it so the magnetizations on the 2 layers are anti-parallel, In that case, the quantum Hall conductivities on the two surfaces are in opposite signs, so they'll cancel. You'll get a Hall conduct of 0 and end up with very high resistance. And that's called the axion insulator state. So all these states have been seen, as I said, with magnetically doped topological insulators, but generally at quite low temperatures. So just to give credit to the first demonstrations by C.C. Zhang, the first measurements were below 30 millikelvin or so, seeing nice quantization and zero conductivity states too. There's been improvements in that time in various improvements in materials quality that have got those the Hall quantization up to originally about 2 Kelvin and very recently up to about 4 Kelvin or so. Very nice work from Rutgers. And there's also been other realizations other than magnetically doped topological insulators, but all those still remain sort of quite low temperature, below 2 Kelvin or so, for where the the quantization of the Hall conductivity is seen. So it's sort of attractive to see if you can get higher temperatures by combining a higher temperature magnet with a topological insulator. You can get magnets of Curie temperatures well above 10 Kelvin or so and try to integrate those with topological surface states. And that's been tried by quite a few groups, but really it's been sort of surprisingly disappointing what you see. There's only one case I know where people have seen a quantization of a Hall signal, and that was below 100 millikelvin. In the graphs here, I show you some of the previous attempts using the same magnet that we're using in our experiments, chrome germanium telluride. It's a van der Waals magnet. And you'll see Jason Petta's group measured sort of resistance changes of less than 1/10 of an ohm, which is way less than a quantized value. Takura's group, in sort of having magnets above and below, only found quantizations about 1/5 of the quantized value at 2 Kelvin. And I'll sort of speculate near the end about why things are difficult with the positive samples. But we'll sort of do essentially the same experiments, but try to make these stacks by just taking van der Waals layers, making the interfaces as clean as we can, and then stack them together and see if we see anything different. Okay. So we get our topological insulator plates from the group of Taylor Sparks at University of Utah. Very nice materials, quaternaries, bismuth, antimony, tellurium, selenium. And this is picked because they have Dirac points near the middle of the single particle gap, and the Fermi level can also be tuned quite near the Dirac point without doing anything special chemically. You can test the quality by making sure that the Hall resistance without any magnet nearby sort of changes sign near 0 top gate voltage, and the resistivity, the longitudinal resistivity, also shows fairly sharp peaks indicating high mobility. If you measure the resistance as a function of temperature, if you sort of gate them right near the Dirac point, the resistance goes up quite large, indicating that most of the bulk conductivity disappears below about 50 or 40 Kelvin or so. Near 0 gate voltage, you can see the contributions from the surface states as well, going down to low temperature. So those are the important starting materials. The other starting material is the magnet. It's a chrome germanium telluride. It's a fairly vanilla van der Waals magnet, an insulator with an out-of-plane magnetization. Okay. So the techniques we use to make the devices are now fairly standard techniques within the 2D community for picking up individual layers and stacking them. What's a little bit different in our devices is that the trick that allows our work to proceed is that we've developed etching protocols to be able to etch through and make well-quantized Hall bars to actually make quantitative measurements of the resistance and Hall conductivity without damaging the sensitive van der Waals layers. So that's what's new that hasn't been done before. So about 2 years ago, we first published some devices where we hadn't figured out how to make these Hall bars yet. So we just had stacks in which we had a little piece of the magnet with a larger piece of the topological insulator on top, and we're measuring sort of the Hall resistance and the longitudinal resistance. We knew those devices were highly shunted because there were current paths for the current to flow through the topological insulator that weren't in contact with the magnetic layer. But already in those devices, we were seeing kind of nice phenomenology. If you look at the Hall resistance as a function of magnetic field, we saw nice square hysteresis loops with good coercivity near zero field. The magnitude of the Hall signal was quite strongly peaked near the Dirac peak as we gated the devices. These are the different curves correspond to different gate voltages. And by looking at the background slopes, we could tell where the Dirac peak was. The slope of the ordinary Hall effect changed as we swept through where we're seeing large signals. But still, the resistance changes were on the order of 10 ohms or so not huge. What's new once you take exactly the same structures and etch them into Hall bars is you get about a factor of 50 increase in the Hall resistance just from eliminating all the shunting from the parts of the topological insulator that aren't in contact with the magnet. So now, once we have a well-defined Hall bar, we see the same phenomenology, but with much larger signals, both in the Hall resistance and sort of these butterfly patterns for the longitudinal resistance that have been ascribed to conductivity along topological edge states. Okay, so this is Hall resistance and Hall conductivity. What you really want to know in terms of thinking about how close are you to a quantized Hall effect is what are the Hall conductivities. So you can just calculate those with the usual sort of 2x2 inversion formulas. I do want to be careful here that because we don't have zero longitudinal conductivity, there are geometrical factors that enter this. You need to know what the length and width of your device is to calculate what the longitudinal resistivity is, and that figures into calculating the Hall, the conductivities as well. But doing the best we can about that, this is what we see. So the Hall resistance, the magnitude of the Hall resistance is a function of top gate voltage on the left here, and the longitudinal resistance on the bottom left, both peaked near the Dirac point. If we take those data and just translate those into Hall conductivity and longitudinal conductivity, this is what we see. So longitudinal conductivity takes the value very close to 1/2 E squared over H over a range of top gate voltage. It's not precisely quantized to part per million values. It's sort of ranging between 0.48 and 0.52 in different devices. But that's also what's seen in the magnetically doped topological insulators that exhibit the parity anomalous state. And that's because you don't have zero conductivity. There's some geometrical factors that are in, and if there's any current in the homogeneities, those will also affect things a little bit. But we're seeing a full value of the 1/2 E squared over H within what we expect to be the experimental uncertainties. We can look at how that varies as a function of temperature. The previous data I showed you were at 4 degrees. We retained the Hall conductivities within a few percent of 1/2 E squared over H, all the way up to about 13 Kelvin or so. And then the Hall conductivity actually remains quite large, all the way up to the Curie temperature of the chrome germanium telluride, which is about 50 Kelvin. The temperature dependence here doesn't correspond to just thermal activation across a fixed exchange gap. We think what's going on is that the exchange gap is decreasing in the range where the Hall conductivity begins to decrease too. But from the temperature dependence, we can set a lower bound on what the exchange gap is of about 4.5 millivolts. And that's a lower bound because likely even where we're starting to see a little bit of change around 10 Kelvin or so, likely the exchange gap is a little bit lower than what the zero temperature value is. But this again is a factor of 100 larger than what's been seen in terms of a quantized value for any deposited proximity effect structure, and even a little bit higher than what's seen for magnetically doped topological insulators. We can get a better value of the exchange gap through direct capacitive measurements. So using the techniques that Emmanuel Tutuk first pioneered for looking at bilayer graphene, and the MIT group is applied to previously to topological insulators too. Essentially, with both top and bottom gates, you can use the bottom surface of the topological insulator that's not gapped as a sensor to detect what happens to the chemical potential in the top surface as you tune the top gate voltage. With that technique and a little bit of algebra, you can map out directly the chemical potential on the top surface as a function of the carrier density. And at the direct point, we see a jump of about 10 plus or minus 2 millielectron volts. So quite consistent with the high temperature scale we expect from the previous measurements due to this exchange gap. Okay, so why are these mechanically assembled samples so different from the top-down deposited samples? Well, when the mechanical assembly, you really do have extremely pristine interfaces. And here's a nice TEM image from David Muller's group at Cornell. And I think what happens is with deposited structures, if you have any intermixing between at the interface, that scattering will push the topological surface state further into the bulk of the topological insulator and decrease the exchange coupling to the magnet. So I think having pristine interfaces really does make a large difference in terms of the temperature scale at which you can begin to see the quantized anomalous Hall effect. Also, compared to magnetically doped topoisolators, these sort of exfoliated samples have much higher mobility, about 10 times higher mobility. That might make a difference too. So far, we've only done magnets on one surface of the topological insulator. It would certainly be interesting to have them on both sides. We're working on that, but that's sort of, this is as far as we've gotten so far. So that was my first story. And I'll now briefly tell you about the second story too, which is trying to look more directly at antiferromagnetic dynamics. And this is challenging because, well, antiferromagnetic generally have high frequency dynamics, but more than that, because of the compensation of the spin sublattices, there's not generally easy signals for detecting what's going on with the dynamics of the spin lattices. We'd like to develop ways of seeing if we can make something useful out of these, which will require both better ability to detect the dynamics on small length scales and ability to start manipulating those dynamics through electrical interventions. And one possible goal we have in mind is thinking about trying to make high frequency nanoscale oscillators that take advantage of the high frequency antiferromagnetic dynamics. So what's been done previously about direct detections of antiferromagnetic dynamics in the frequency or time domain are a variety of techniques, some electrical, like resonant absorption or spin pumping techniques, and some optical. But what's been done so far, at least in terms of electrical techniques, is all involved macroscopic millimeter scale samples. And so one of the things we want to do is see if we could scale things down and get reasonable signals from much smaller samples. So the technique we had in mind was taking advantage of work by other groups on making tunnel junctions in which antiferromagnets were the barriers, the tunnel barriers. And there's been lots of nice work showing that in DC measurements, you can detect changes in the magnetic orientation between spin sublattices in van der Waals antiferromagnets by looking at their tunneling signal. So we wanted to take this work and see if we can sort of look at the high frequency signals as well once we start exciting the magnetic dynamics. And this requires some changes from what's been done before, mostly in the way of microwave engineering, and that you want to reduce the impedance of the junctions so that they're not too far from 50 ohms. And you want to reduce some of the nonlinearities that are naturally there so you don't have large background signals. I won't go into too much detail about that, but those are some of the things we've had to worry about. Okay. So we've studied the van der Waals antiferromagnetic chrome sulfur bromide, which is a nice antiferromagnet, lots of interest for lots of reasons. For us, it's interesting because it has reasonably strong triaxial anisotropy, which allows us to control the directions of the spin sublattices in nice ways with external magnetic fields. To begin our work, we wanted to know where the modes were, and so we did some of these macroscopic experiments, just resonant absorption, trying to understand what the different modes are, just using coplanar waveguides. And so we were able to characterize what the antiferromagnetic modes are and understand all the magnetic parameters, the anisotropies and exchange fields that govern these modes. If you apply an external field parallel to the in-plane easy axis, you can see right-handed and left-handed modes in nice ways. If you apply a magnetic field instead perpendicular to the easy axis, you instead see acoustic and optical modes. But all these can be understood in kind of a Landau-Lifshitz-Ginsburg kind of way. In the experiments on smaller scale devices, we'll mostly work with magnetic fields perpendicular to the z-axis, and we'll be detecting the optical mode, because that's the one that changes the relative orientation of the spin sublattices and gives magnetoresistance signals. Okay. So once you try scaling things down to much smaller size scales, this is kind of the geometry we have in mind. It's a 3-terminal tunnel junction. On the bottom is a metallic conductor layer, platinum telluride, chosen both because it's metallic, which reduces the overall tunnel junction resistance, and it has reasonably strong spin-orbit coupling, so we'll be able to apply spin-orbit torque here in a few slides. The middle layer is a bilayer of the chrome sulfur bromide, and chrome sulfur bromide is an A-type antiferromagnet, ferromagnetic within each plane and antiferromagnetic between them. And so we have a 2-layer antiferromagnet as our barrier, and then the top layer is just graphite for making easy contact. And in DC measurements, we can measure sort of how the resistance changes as we change the relative orientations of the spins in the spin sublattice. Okay, so how do you measure the high frequency dynamics? Well, we use an offshoot of spin torque ferromagnetic resonance. We'll apply a high frequency AC signal through the bottom channel that will excite the antiferromagnetic dynamics both through Oersted fields and possibly with some contribution from spin orbit torque. And then we'll detect the dynamics by having some AC current going through the tunnel junction that will mix with the resistance oscillations and give us a resonant peak at a DC voltage. So just looking at the raw data, once you've sort of worked out the microwave engineering, you see resonant dips here due to this DC mixing signal at both positive and negative field corresponding to when the magnetic resonant dynamics are resonant with the applied AC field. And you can map out what these modes do as a function of magnetic field applied with various angles. And from that, work out what are the anisotropy and exchange parameters for the 2-layer magnet and compare that to the bulk. We've done that. The anisotropy fields are pretty much the same, a little bit different. And the exchange field is quite different, almost a factor of 3 lower in the bilayer. But we think that comes from not having layers on both above and below each magnetic sublattice, so you expect a weaker exchange. Possibly also there's some charge transfer from the layers that make the interactions a little bit different as well. So we've also begun to look to see if we can manipulate these electrical modes through spin-orbit torque from the bottom channel. We're working here in analogy with spin-orbit torque in ferromagnets. In ferromagnets, you see that a spin-orbit torque can change the resonant line width of a ferromagnetic resonance when the spin due to the spin-orbit torque is parallel to the precession axis of the magnet. And we've seen something similar here with the antiferromagnet. What we've done is apply a magnetic field sort of oriented along the hard axis, but with the crystal oriented, so that's 45 degrees away from the current in the channel. With that magnetic field, we can tune the spin sublattices either parallel or perpendicular to the spin generated by the spin orbit torque and see what effects are produced by current, whether we change the line width or not. And what we see is an effect that's asymmetric in the direction of magnetic field, in the sense that for one direction of magnetic field, we see a strong dependence of the line width on current, indicating that the spin orbit torque is modifying the line width of the resonance. For the reverse magnetic field, there's essentially no effect. And we can explain this as to whether or not the spin sublattice adjacent to the bottom channel is parallel or perpendicular to the spin generated by the spin orbit. For one orientation of the magnetic field, for a particular value of field, we can generate that spin parallel to the spin orbit torque. That's the situation where we see a strong dependence of the line width on the current. For the opposite direction of magnetic field, we turn the spin sublattice of the other lattice parallel to the spin axis of the spin orbit torque. But the spin sublattice adjacent to the bottom channel turns perpendicular. For that, we see essentially no effect of the spin orbit torque on the line. And with the magnetic field, we can also switch the direction of the spin sublattices. If we do that, we see the opposite effect, the asymmetry in the magnetic field switches sign, as you'd expect from this picture. So we can look at the dependence, how strong the current effect on line width is as a function of the angle of the spin sublattice adjacent to the bottom channel. There's a nice cosine dependence there, indicating essentially only that angle matters in terms of the strength of the tuning of the line width. The spin orbit torque only acts on the spin sublattice adjacent to the bottom layer. A negligible amount penetrates through to the second layer, which is sort of just kind of interesting and just showing how local a spin orbit torque can be on this sort of layered material. Okay, so those were the two stories I wanted to tell. I'm happy to stop here and answer questions. Just after giving credit to the people who are really responsible for the work on the topological insulator was led by Rakshit Jain, who's looking for a postdoc now. If people are interested in a very good student, along with the younger student, Matthew Roddy. And the work on the antiferromagnetics was led by Talmin Cham, who's now a postdoc at Caltech. So this is where I'll stop.
Thank you, Dan. And we have time for questions, please. Thank you so much, Dan. And I guess next we have Professor Chang Liu from SUSTech in China. And he's going to tell us about spectroscopic discovery of spin split antiferromagnets.
So I would like to share the screens. Can you hear me?
Yes, we can hear
Okay.
you. We can also see you.
So what can you see right now? Or is this the so right now it's the because okay, is that fine now?
Yeah, very good.
Okay, great. So yeah, thank you, Shu Yang, for inviting me to this very nice workshop here. So today my title is the spectroscopic discovery of spin split antiferromagnet. What is the relation between the spin split antiferromagnet and the Altermagnet is that some of the things that have spin splitting induced by AFM is not an Altermagnet, but they are not collinear. They are not even coplanar. So what the difference here is that the material we are trying to we are discussing right now is not an Altermagnet, but well, by definition. But the problem is it's shared the same physics, almost the same physics. So yeah, I would like to first introduce the collaborators of this work. First, the theory is done by Chi-Hang Liu's group also from SUSTech, and the spin apparatus is mainly done from Chao San's group in Shanghai and Huang Yaobo's group in Shanghai Synchrotron. So this is one of the lab devices, and this one is the beamline in a synchrotron. So also the ARPAS is done by these groups, and the scanning NV magnetometry is done by the group in U Stuttgart. The problem is we need to figure out the size of the domain of the antiferromagnetic domain in this compound. So we need to do this to see what's going on there. So here's our outline. Here's my outline. First, I will introduce a little bit about the so-called unconventional antiferromagnet, and then I would like to talk in detail about how we do the spectroscopy in one of the spin split antiferromagnets, which is the manganese ditelluride. And then, if time permits, I'll go on to discuss other unconventional antiferromagnets, our data on them. So yeah, the first part is that so the motivation of this work is twofold. First, there is always a dream of finding the ideal next generation spintronic materials. We know that both ferromagnets and antiferromagnets are used in spintronics, but they have incompatible advantages and disadvantages. For example, ferromagnets have macroscopic residual polarization, so they have straight fields and can be easily controlled by external probes. Antiferromagnets have no stray fields, so the polarization of each domain is not easy to manipulate. However, this property also makes them stable against environmental disturbance. Now the question is there can we find a magnet that incorporates the advantages of both ferromagnets and antiferromagnets? Thanks to the recent works by several theoretical and experimental groups, we can now give a positive answer to this question. This figure is not adopted from the previous speakers, Dr. Smigol, and from an article in Science. We can see that when the sublattices of an antiferromagnet is not linked by translational symmetries, but by other symmetries such as the rotational symmetries, the spin in the AFM materials splits and give rise to spin polarized charge densities in the real space and the spin splitting of energy bands in the K space. So we call this spin split antiferromagnets as compared to the conventional antiferromagnets whose spin are degenerated. It should be noted here that the term Altermagnet refers to the collinear part of the spin split antiferromagnet. In this magnet, spin split antiferromagnet, different springs respond differently to the field, to the applied fields. So the orientation of the moments can be controlled easily by the external fields. In this sense, they have similar physical properties as the ferromagnets, and it's possible to replace the ferromagnets as core materials in spintronics. So now we examine the terms that are often appear in the field of unconventional antiferromagnets. So in the past years, we started to recognize that some of the antiferromagnets exhibit properties that usually appears in ferromagnets instead of antiferromagnets, like the anomalous Hall effect and the spin splitting and so on and so forth. Here we loosely define the term unconventional antiferromagnet to be all the AFMs that show such unusual properties. Therefore, unconventional antiferromagnets include spin split antiferromagnet, the AHE antiferromagnets, and etc. So the spin split antiferromagnets can be divided into two parts: the collinear Altermagnet and the non-collinear or even non-coplanar spin split antiferromagnets. Magnesium ditelluride belongs to this not collinear part in this categories. Both the collinear and non-collinear parts share the same momentum-dependent spin splitting induced by magnetic exchange coupling. On the other hand, the anomalous Hall AFMs are not necessarily Altermagnet, and some of them even have no spin splitting. In other words, spin split AFMs are a subset of unconventional antiferromagnets, and the Altermagnets is a subset of spin split antiferromagnets. While the area of the anomalous Hall effect antiferromagnet spans several regions. The compounds we are discussing today, magnesium ditelluride, sits here in this graph, meaning that although it is spin split, it is not an Altermagnet by definition. It will have the AFM-induced spin splitting. So another motivation of our study comes from the group theory side. We can see from this figure that if a condensed matter system contains both magnetism and spin orbit coupling, its Hamiltonian can be fully described within the magnetic double space group. If we eliminate the term of spin orbit coupling, it turns out that the Hamiltonian must now be described by a much larger term, a much larger group called the spin space group. This group have not catch enough scientific attention until very recently. The main difference between these two groups is that the spin and the orbital degrees of freedom is totally coupled in the magnetic double space group, while they are partially decoupled in the spin space group, meaning that in a legitimate operation in this group, the angle of spin rotation can be different from the angle of lattice rotation. We mark these angles theta and phi here. So while the two angles are the same theta here, in the case of magnetic double space group. So here we give a simple example on the elements of the two groups. We want to find, first in this graph, we want to find an operation that keeps both the lattice and the spin unchanged in this simple antiferromagnetic arrangement. In the framework of magnetic double space group, we have the C2 rotation for both the lattice and the spin. Let's see here. We have the C2 rotation here. And then, however, such rotation is not a symmetry operation of this system. We can see from this that this is not equal to that. So it's not a symmetry operation of this system. However, in the spin space group, we have several operations that can describe the symmetry of this system, like the C2 rotation of the lattice only. So look like this. C2 rotation of the lattice only and keeping the spin unchanged. And then we have another type of operation that is the lattice C4 rotation plus the spin C2 rotation. So we do 90-degree rotation of the lattice first, and then 180-degree rotation of the spin. Well, for some reason, this is not 180-degree. That's okay. Yeah, and this operations contains separate rotation angles for the lattice and the spin, and allow for the spin splitting in antiferromagnet. Yeah. So here, the spin base group, the theory of the spin group is developed in the 1970s. In 1966, and there are two papers dated back to 1966, and one paper here by Litwin dated back to 1977, as Dr. Smigel just said in the previous talks. And now we have more development on this spin group field, especially in the year of 2022. So Qihang Liu's group calculated the total number of the collinear spin point group and the coplanar spin point group to be 90 and 253. And this number 598 here corresponds to all the spin point group, the element number of all the spin point group. And this is done by Litwin in 1977. And these three papers, again, they continue to advance this field by enumerating all the spin group elements in the spin space group instead of spin point group. So there are a lot of elements here, much larger number compared with this 1651 magnetic space groups. So these three numbers are recently published in PRX. So very recently published. So we have a lot of unique characteristics of such spin splitting. First, it is irrelevant to the presence of spin orbit coupling. It is a non-relativistic effect that has an energy scale 1 order of magnitude larger than the SOC. Second, the spin and the orbital part is partially decoupled, as we mentioned before. Third, the calculations show that such spin splitting is anti-symmetric about the high symmetry planes in the Brillouin zone, having an alternative spin pattern. In magnesium ditelluride, we call this a plate-like spin texture. Fourth, in some of the spin split antiferromagnets, the splitting can change sign between the plus and minus Kz, forming a Hamiltonian that contains quadratic terms in K. So yeah, as to the possible potential applications, for example, in these papers by Dr. Smigel and collaborators, we see that altermagnets can produce spin currents that are perpendicular to the charge current, convenient for spintonic devices. Also, the heterostructures made by altermagnets can realize giant magnetoresistance and spin splitter torque. The splitting of spin also leads to the chiral splitting of magnons, as just mentioned by Dr. Smigel as well, which can be probed by this by this, for example, the spin Seebeck effect. So this is the property of some typical spin split and antiferromagnet. So the first one is magnesium ditelluride, and this is magnesium monotelluride, and this is CRSB, and this is ruthenium oxide. So yeah. And for example, the sizes of the antiferromagnetic domains turns out to be very important in the APES measurements, since the average spin signal from several domains will significantly weaker than that from the single domain. Based on our scanning NV magnetometry measurements, we argue that the domain size in magnesium ditelluride may be large enough for the detection of a substantial spin signal here. So right, so we go on to discuss our work here. So these are the main contributors of this work. Professor Shan Chao actually made the device, make the APES device to make this project possible. So yes, so this is the basic structural and magnetic properties of magnesium ditelluride. It's not a collinear magnet, so it's not an altermagnet. The unit cell looks like a cubic unit cell, but it actually has no C4 symmetry around the KZ axis. It actually has a C3 symmetry along the body diagonal direction here. So yeah, the new temperature of this antiferromagnet is 87 Kelvin. This is very clear from our measurements. So yeah, so the spin splitting here is irrelevant of the SOC. So we can see that without the SOC, it has already spin splitting very large. So with the SOC, the spin splitting just shift a little bit instead of enlarge or shrink. So it just shift a little bit. So with and without SOC, this compound has spin splitting that is induced by AFM order. So yeah, so in theory, we have the spin texture derived in DFT theory. So this the arrow here corresponds to the in-plane component of the spin, and the color here corresponds to the out-plane components of the spin. So you can see that the in-plane component of the spin is antisymmetric with respect to these two lines. So yeah, here also with antisymmetric with respect to these two lines. Here, this one is the KZ equals to plus 0.2 pi, and this one is KZ equals to minus 0.2 pi. So between the plus KZ and the minus KZ, the spin also change sign. So this is the different the characteristic of this type of spin splitting that is different from the Dresselhaus and the Rashba spin splitting. So it also happens in the bulk bands, not the surface bands, as the Rashba splitting does. So yeah, first of all, we would like to tell you that our APES measurement actually measures the bulk band instead of the surface band, because the spin splitting in the surface band is irrelevant to our discussion, right? It's not a property of the antiferro of the altermagnet. It's not a property of the spin split antiferromagnet. So we can see from this figure that it has KZ dispersion, meaning that the bands we see are actually comes from the bulk of the crystal. Although the intensity here is a little bit broad, but we can see from this one that this has a cross-like shape here, and this has a something like a ellipse here. So it changes from nothing here to an ellipse here with different photon energies. So we believe that we are probing actually the bulk bands. So here, this is detail, we skip that. And we collect 3 types of evidence for the plate-like spin splitting in this compound. First of all, at a single KZ, corresponding components of spin is antisymmetric about the high symmetry lines. So this corresponds to this part of the effective Hamiltonian. So this part is the exactly the same as the Dresselhaus part, Dresselhaus type spin splitting. So we need to confirm the in-plane spin texture is Dresselhaus-like. instead of Rajba-like. So this is the details about our spin detection. We will skip that. And this is our data. So first of all, we would like to cut these two lines here and do a S-APES measurement, the spin APES measurement. The green, the blue and red here corresponds to two different types of spin. We can see from here that the when we cut in along cut 1, it has like the top is blue and the bottom is red here. When we cut along cut 2, the top becomes red and the bottom becomes blue here. So it is exactly anti-symmetric with respect to the ky equals to 0 line here. So it's also it's also consistent with our calculations. So next we do the cuts 3 and cut 4 here. Instead of
quick question.
okay. So here,
what does blue and red mean here? It's which direction of the spin are you measuring?
SX, I forgot to mention here. SX means here, this direction.
Okay.
Yeah, this
I
direction.
see. Okay.
Yeah. Okay. So yeah, in our DFT calculation is left blue and red red to the right, and in our APES measurements it's also left one is blue and the right one is green, red. So it looks like a little bit noisy in all of this data. That's because the efficiency of the spin detection is very low. Each graph here takes about 14 hours, and the sample stay alive in the vacuum chamber for like 24 hours. So for each sample we can take like 1 or 2 of these cuts, and that's it. So this is not a very easy measurement to do. So we continue to do cut along 1 and 4 here. So according to our DFT calculation, it has this type of red and blue texture here. And for some reason, we can see this band instead of this band. This band is not seen here in our data, but I don't know why, but it's probably the matrix element effect. And here we can see that the blue comes to the top and the red comes to kind of the bottom, and it's still consistent with our calculation. So this one is we are measuring SY right now. So instead of SX, we are measuring SY right now. So the device we are using can measure both directions. So right. So yeah, we are cutting along more directions, which we are not talking about. We will not talk about in detail in this talk. Yeah. So basically, it confirms that the in-plane spin has a Dresser house type texture. So the second evidence for the plate-like spin splitting is this part of the Hamiltonian, which means that if we change the sign of Kz, the entire spin will change. So we can see from this cartoon here that if we change to Kz minus equals to Kz is less than 0, the red spin will become blue and the blue spin will become red. So we actually did this in a in the Dreamline in Shanghai. So this is also not a very easy measurement to do because a lot of those machines are broken at the same time at that time. So we wait until like half a year later to do this measurement. So yeah, so this guy is supposed to be blue here. We measured it to be blue, and this one is supposed to be red here, and we measured it to be red. So everything fits good. And we even changed the polarization of the incoming light to make sure that this is not what's called a final state effect in the APES measurements. So when we changed to another photon energy, the Kz plus changes to Kz minus, and then the left the red one changes to blue one, and the blue one changes to red. So everything fits quite well actually. And we actually have more data on another brilliant zone. So at 82 electron volt, this guy is red, and at 66 electron volt, this guy is blue. So we using systematic Abas measurements, we can make sure that the KZ, when the KZ changes, the polarization will change sign. So the third evidence for the plane line spin splitting is something corresponds to the temperature. When we are at the low temperature phase, the spin is very apparent here. When we are approaching the high temperature paramagnetic phase, the spin becomes weak and then eventually disappears when it goes up, goes above the Tn. So this one is 30 Kelvin and this one is 150 Kelvin. Remember the Tn is 87 Kelvin here. So we can see that above 87 Kelvin, it has almost no spin polarization. So yeah, this is the summary for our work. So we collect 3 different evidences to give the conclusion that the spin polarization is K dependent and SOC independent, and the spin texture is plate-like. So we kind of discovered that there is some of the antiferromagnet has spin splitting. So if I think we are out of time, right? I'm out of time now. Oh no,
little bit time.
not yet. So maybe a little few 4 more minutes. I can talk about a little bit about our another work of ours and lead by the student Meng Zhang here. And this work is the chromium antimony. So we have a paper talking about the chromium antimony, the Abas data on chromium antimony. You can see here that the spin splitting is kind of visible. But the problem is it's not that visible actually. So there is a yeah, so this data is not very optimistic. So a lot of groups try to repeat these measurements to bring better data to this compound, including our group. So yeah, our data is like this. So in this kind of cutting plane here, we cut 5 different photon energies. So we cut 5 different photon energies according to the theory of Altermagnet. Also, this guy is an Altermagnet. According to the theory of Altermagnet, it has no spin splitting along gamma M and has no spin splitting along AL, but it will have spin splitting in between these 2 high symmetry lines. So in along gamma M, we actually don't see spin splitting here, and along LA here we also don't see spin splitting, but in between these 2 high symmetry lines, we see quite clear signal of spin splitting here. The problem that we didn't do a spin resolve measurement in this compound is that we tried to do it, but it gives 0 signal. So yeah, we guess that's because of the domain size is not very big in this compound. So maybe the domain is not large enough for us to tell to do the S-Abas measurement. So for the in-plane components, for the in-plane directions, we also cut from cut 1 to cut 5 here. In cut 1 and cut 5, we will not have spin splitting by definition. Oh, okay. Oh, sorry. Along cut 3, we will not have spin splitting, but cut 1, 2, 4, and 5, we can see spin splitting here. So these guys are quite, yeah, clearly spin splitting. So we will, yeah, this paper is about to publish in this journal. So this data is also repeated by other groups. This group is from Zhejiang University in China, and this group is from USTC in China. They are published. They will be published in PRL. And this paper is from the Swedish group in Max4. So yeah, so these are the data from other groups on CRSP. So that's all for my talk. Thank you very much for listening.
All right, so let's get started. So in the afternoon, we will first have Professor Rafael Fernandez. I think you just moved, right?
Yes.
Now in University of Illinois Urbana-Champaign, and he will talk about topological properties of altermagnets. Please, Rafael.
All right. Thank you very much for the invitation to be in this very interesting workshop. Yeah, so I want to talk a little bit about topology in altermagnets, and I'm essentially going to talk about two different works. One that I've done with my collaborator Turan Birol, my former postdoc Benildo Carvalho, and collaborator Rodrigo Pereira in Brazil, and then a more recent work with Joran Vanderbos, that is in Drexel, and Daniel Antonenko in Yale. I know that you heard a lot about altermagnets. I want just to go over a little bit about mechanisms coming from a more correlated electron approach, and then I'll talk about how spin orbit coupling can enable some interesting topological effects in these materials. All right, and for a recent review, together with Libor, Tomasz, and Heido, just posted this week a review that you may find interesting. Okay, so again, I will start with a very brief overview, just so we're all on the same page. The question that we want to ask is what kind of symmetry I have that when I combine with time reversal leaves a magnetic system invariant, and assume that we have no spin orbit coupling. So I'm really talking about combining crystalline symmetries with spin symmetries. And if I have a ferromagnet, there's no such symmetry, right? If I apply time reversal, I flip the spins, there's nothing I can do that brings me back to where I started. And as a consequence, as we know, the symmetries that make the spin bands degenerate are no longer satisfying, and you get a spin splitting of the bands, okay? Now, in an antiferromagnet, the situation is different, because if I flip the spins, blue goes to red, red goes to blue, it's clear that if I do a translation by a unit vector, by lattice vector, I'm sorry, I recover the same magnetic configuration from which I started. So T prime, which is just time reversal plus translation, is a symmetry. And because T prime does not, because translation does not affect momentum, you still have the condition satisfied for a spin degenerate band. So even though you have long-range magnetic order, you do not split the bands. Now, let's go back to this case, and let's say that now, for some reason that is not related to electronic interactions, but crystal field interactions, crystalline interactions, the local environment of these two sites are different. Right? And I'm representing these by these losangs here. So you can think of these as an octahedron, or as a cage, something that comes from the lattice. And they, as you can see, they are related by a 90-degree rotation. So because of now you see that the unit cell has twice as many atoms as the one that I started. And if I now have anti-parallel order of the spins, I no longer can apply translation to undo time reversal, if you wish. And that's because, as you can see, the magnetic order does not break translational symmetry anymore because of this effect of the crystal. So that is not the same as an antiferromagnet. But what you can do is actually do a 90-degree rotation in the lattice, and because of this, you can see now that you recover the same magnetic configuration from which you started. So time reversal combined with rotation is a symmetry, and that is what I classify as an altermagnet. And this, again, I'm sure you heard it in Libor's talk, started back in 2020, formalized a little more a couple of years ago, and continues to evolve. And the key point now is that spin degeneracy bands is no longer guaranteed. In fact, bands of opposite spin are related by rotation. So generically, actually, you're going to have a splitting between spin up and spin down, except along the directions or planes that are kept invariant under the rotations. So general consequence of that is that your Zeeman splitting or your spin splitting will have nodes. And for example, you could have nodes that are along the main axis. So in general, you'll get some sort of nodal spin splitting structure It could be a D wave form factor, but as pointed out, could also be G wave, I wave. Any even parity modulation can happen. And again, this follows from the symmetries of the system. And one of the appeals of this idea was from of the fact that it realizes what's called non-relativistic spin splitting. There are previous works that also have pointed out that this could happen in specific materials. But the main idea here that is that the splitting, and as we're going to show, can be much larger than any scale, electronic scale, and it doesn't require spin splitting. So that's why it's different than other, for example, non-collinear magnets or non-central symmetric systems that have a spin splitting that depends on the spin orbit coupling. And so if you want a brief summary, you have three classes of magnetic ground states. And again, it depends on which symmetry do I combine with time reversal to get the system invariant. No symmetry is ferromagnetism. If it's translation, or actually if it's inversion, both work the same way. You get no splitting. And in altermagnetism, you get a rotation. And when I say rotation, it could be proper, improper. Most times it actually is combined with a half translation. So it's a non-symmetric operation. The spin splitting acquires momentum dependence that is even in momentum. Okay. Now this, Libor, Heidel, and Thomas put this in a very firm formalism by showing that if you considered collinear phases, and instead of focusing on what we are more used to, which is magnetic space groups or magnetic point groups, which there are 4 types, we understand them well, but in those, you assume spin orbit coupling since spin transforms according to the same symmetries, or transforms according together with the lattice. There are spin groups which you decompose how spin and lattice transforms. They are independent rotations. And in this paper, they very nicely show that there are 3 types of spin groups, and each one you can associate one of these things. Okay. And since then, there have been a lot of advances in understanding spin groups, which I'm not going to talk more now. It was pointed out that there is a clear connection with multipolar magnetism. So if you expand distribution of magnetic dipoles, the first 3 moments you get a magnetic dipole, a quadrupole, or an octopole, and you can see right away that each one of them is connected to a different kind of Q equals 0 magnetic order, right? So you get quadrupole is intra-unit cell antiferromagnetism connected by inversion, like what you would get in a honeycomb lattice with opposite spin order. And you can see the similarity between this distribution of spins in the unit cell and a magnetic octopole moment. While it's true there's some symmetrical characteristics that are shared between them, it's important that there's also additional multipoles that contribute when you think about the outer magnet, and I'm not going to discuss much about, but this is just to establish a first connection with a topic that has been studied a lot in F-electron systems, where you look at non-Kramer's doublet ground states, and you can form pseudospins that transform not as dipolar moments, but like as octopole moments. So there is a connection of the symmetries of these phases. And the main idea is now that with the symmetry considerations that are prescribed with this spin group analysis, you can find materials from databases that have these properties. And as I believe was discussed before, rutiles is one of the main candidates. Manganese difluoride has been very widely studied since the 80s. Ruthenium oxide, there are still some controversies of whether it's even magnetic or not in stoichiometric form. And right now, there are, I would say, 3. So this is a plot from their paper showing the size of the spin splitting and the critical temperatures. And you see that these 3 guys here, chromium timonide, manganese telluride, and ruthenium oxide, they have the highest spin splittings above room temperature phase transitions. And they, of course, I mean, because of these reasons, they have been also studied more extensively experimentally. Manganese telluride and chromium timonide, recent ARPEs, including spin ARPEs measurements, I think show very clear evidence for the altermagnetic character, whereas with indium oxide, there's still debate going on, and I'm not going to talk too much about it. Okay, so now I want just to bring a little bit to connection to, I come from a correlated electron community, to a concept that has been very much investigated in the community, and try to understand what are the differences or similarities between altermagnetism and this instability. So back in the late 50s, Pomerantchuk formalized the theory of what are the instabilities of the Fermi liquid. We all know that in the presence of any small attractive interaction, it's unstable towards a BCS instability. But what Pomerantchuk was looking for were instabilities in the particle hole channel, meaning magnetic order, orbital order, or charge order. Okay? And the idea is that you start with the quasi-particles of the Fermi liquid, write down the interaction and project it into different angular momentum channels. So that's the L, and you can also consider it in the spin singlet or spin triplet channel. Okay? And there is a generalized toner instability, if you wish, that tells us if these interactions overcome a certain threshold. The negative here is just because these are attractive interactions. But if it overcomes a certain threshold, then the system is unstable towards one of these instabilities in the corresponding channel. And notice that the higher angular momentum, the higher would be the threshold. So if you look at that, what are these channels? Well, some of them are very well known and understood. If you look in the singlet sector and the charge sector, you can generally write the charge density as a spherical harmonic or a Legendre polynomial. And if you look at the L equals 0 channel, this would be nothing but an expansion of the Fermi surface, which is not allowed because of Letchinger theorem. Yet you can use this as an indication of phase separation. L equals 1 would be if you had such an instability, you would acquire a spontaneous charge current in the system. As you can see, the Fermi surface now displaces a little bit from the center. And L equals 2 is what some of us, including myself, have worked for a while, which is the nematic instability. So the circular, the isotropic Fermi surface now is no longer, it becomes anisotropic. Okay? Now, if you look at the same instabilities now in the triplet channel, right, we again see right away that the L equals 0, spin up and spin down bands move differently, or they have a relative chemical potential. That's nothing but ferromagnetism. And that's what I mentioned, that the first, the Stoner instability, the Pomerantchuk criterion for instability is to some extent an extension of the Stoner criteria. Okay? L equals 1, you see that you get a spin current because spin up and spin down Fermi surface move differently. Okay, and L equals 2, you see something that looks a lot like an altermagnet. You see that spin up bands deform in one direction, spin down bands deform in the other direction. So each spin channel breaks the symmetry of the lattice, but together, when they are combined, you can recover the symmetry, right? These states have been studied, but a little less. The L equals 1 has been discussed actually back by Jorge Hirsch about 35 years ago. And the L equals 2 was discussed also in this very nice paper by Eduardo, Shuzhen Zhang, Gong Jun-woo, and Kai Sun discussing the properties of the system. It is very clear that from a symmetry perspective, if you just focus on symmetry, the symmetries of the L equals 2 Pomerantchuk state are equivalent to the symmetries of an altermagnetic state. Okay? You can write down the spin density as, again, as a D wave or G wave or whatever form factor of your spin. Okay? And so there is this interesting connection. Now, what is important is discussing, and I think that's the main insight of these advancements in altermagnetism, what are the differences in respect to mechanism? Two systems can have the same symmetries, but have different microscopic mechanisms. And that's where I would like to go a little bit in more detail, because this also helps us appreciate what is being discussed in the context of altermagnetism. So as I mentioned, for Pomerantchuk instability is a purely electronic instability. And you have, again, it's not a weak coupling effect. you need to overcome a threshold, okay? There are issues with the L equals 1 channels because of conservation laws, and this being widely discussed in these papers more recently. And the L larger than 1 stabilities, including what would be equivalent to the Altermagnet, the main issue of finding microscopic models or materials is that how can you ensure that these, not only that the interactions overcome this threshold, but this happens without all the other angular momentum channels, including the L equals 0, happen at the same time. So it's been very elusive to find these states, especially the spin spin triplet ones in models. And what altermagnetism does, that's one point we cover in this review, is it essentially divides the problem in two. So you let electron interactions do one part of the job, which is making the spins anti-align, essentially, roughly, okay? And you let the crystalline interactions do the rest of the job by creating different but symmetry-related crystalline environments for these anti-parallel spins. So it is this, it is both of these interactions acting together that enables altermagnetism. And I want to mention here, showing an explicit example, so you see how this happens and why it matters for the sizes of spin splittings that we're looking for. So I like little models, so let's start with a model just to explain how this appears to you. Let's start with an antiferromagnet. And now I'm going to artificially, just by imposing it, saying that my new unit cell now is the dashed one, which has 2 atoms per unit cell. And I rotate it for simplicity, so you get this lattice here, okay? So as you can see now, just because I imposed it, the new unit cell has 2 atoms that are related by 90 degrees, right? We can go ahead and write down an effective Hamiltonian for this problem. And you have 2 different degrees of freedom, the sublattice, which I'm going to call tau, the spin that I'm going to call sigma. And I'm going to do a very simple model where the spins, I have both local moments, if you wish, on the sites, that's the N, the staggering magnetization, that are condo-coupled to electrons that are just hopping around, right? And I put here nearest neighbors and next nearest neighbors. You can write down this model, and if you solve it, you find that nothing happened. The spin bands are still degenerate, okay? And you can see here, you probably cannot really see, but the blue and red bands are on top of each other. There's a splitting that is set by this condo coupling, but that's it, okay? You didn't split the bands. And the issue is because I actually haven't imposed or implemented the symmetries of this lattice. Just by writing down in a bigger unit cell does not impose that. I need to have something else. The lattice needs to enforce the symmetries on these atoms. The easiest way to do that, or at least in my opinion, is to include these non-magnetic atoms that I'm putting here. And when you do that, you immediately realize that these 2 next nearest neighbor hoppings have to be different. This one goes through a non-magnetic atom, and this one doesn't, okay? And this, I'm going to call this difference here TD, and you can see that this is nothing but a realization of the Lib lattice. If you work on cuprates, you can see, immediately recognize here the Emery model, but it's kind of inverse because we're interested in the oxygen and having the copper bands, if you wish, be high energy, okay? But now, if you implement, again, this crystalline effect that I have, these symmetries imposed by the crystal, I have a new term in my Hamiltonian, I'm sorry, and what you see is that you open now a gap between spin up and spin down bands, okay? Or splitting, not a gap, okay? And this happens everywhere in the Brillouin zone except along the diagonals, and you get the D-wave altermagnet. Now, what I want to point out to you in this simple example is that you notice that there are 2 different energy scales in the problem. The spin splitting is actually not determined by the condo coupling, but is determined by the hopping anisotropy. That's the effect of the lattice that I was pointing out before, and that's why you can get very large order EV spin splittings, because it's coming from this. Whereas here, of course, even though I'm saying that here, I artificially set the condo energy to be large, so you can see the splitting, okay? Now, you can say this is just a very simple example, but Igor and Libor actually have a very nice paper showing that if you have monolayer iron selenium, because the monolayer, the interface effect that you'd have, making arsenic, selenium up and down different, you essentially have such a model, okay? All right. So I think that what I'm trying to come across here, especially for those of us that are coming from a correlated community, is that there are similarities with things that we've been thinking about, but there are also important differences, especially about mechanism. And one interesting thing is that once you think in this direction, you no longer need to be focusing only on Fermi liquids. You can also focus on insulators. And that actually brings us to opens a new class of altermagnets that are Mott-insulating altermagnets. Okay, so I think and this is already pointed out in different contexts, but these perovskites ABO3, which most of them are Mott-insulators, right? They have Niel type or G type antiferromagnetic order with alternating spin up and spin down. This comes again from essentially Mott physics. And in the ideal perovskite structure, which is cubic, it's really antiferromagnetic order with the spins up and down, as I'm pointing here. The green are the oxygen, okay? But now comes the magic of the lattice, and in this case, chemistry, because to accommodate the cation, the A atom, okay, a lot of these perovskites actually have to, most of them, the vast majority of them will deviate from this cubic structure. And a subset of them actually go to an orthorhombic structure that goes by the space group PNMA, where the oxygen have these two rotation patterns that form now a bigger unit cell that that now have more atoms. There's actually 4 instead of just 1. And especially what happens now, and I can walk you through that, is that the new unit cell, which is this one now, has spin up and spin down. And these atoms are actually not related by rotation, by inversion, but are related by a screw axis, which corresponds to a rotation plus a half translation. Okay? So this is just to show that you have this interplay now, even in strongly correlated systems where you can get that. Now, there's an extra ingredient in the Mott insulators because these oxygen octahedral rotations also impact the orbitals. And this, I think, is a point that's being exploring. Okay, now I want to focus a little bit on topology. And for that, I need to bring back spin-orbit coupling, okay? Spin-orbit coupling, we know what it does. It essentially now makes, whenever I do a rotation in spin space, the spins also have to rotate. And that, for example, if I have a 180-degree rotation axis, the result on the spin depends on the direction of the spin with respect to the axis, okay? We know very well what happens in ferromagnets. The spin-orbit coupling will force the moments to point along certain high symmetry directions. But what about an altermagnet? So as I mentioned, right, without spin-orbit coupling, you write down the spin density as an overall form factor, d-wave form factor times the spin. But what happens when you have spin-orbit coupling, and what we showed here, and I'm going to give examples, is that now what happens is that different spin components will acquire different d-wave form factors, okay? This is not a summation, okay? This is just fixing a direction, okay? And what it means generically is that all components are generally modulated, and that in several cases you're going to induce a ferromagnetic moment. But the point I'm going to focus a bit more is what impacts these nodal planes or the nodal directions under which the spin splitting is 0. So to give you an example of how this happens, consider the case of a rutile, for example, manganese difluoride. And I'm going to do, so it's a tetragonal lattice. I put a d-wave form factor here, kx, ky. Okay? If I turn on without spin-orbit coupling, the spin transforms as irreducible representations of SO3 or SU2. And now, but when I turn on spin-orbit coupling, they will actually have to transform as irreducible representations of the tetragonal group. So, and now if the spin points up, points along z direction, is A to G. If it's X and Y, is EG. What does it do? Well, let's assume that it points, the spins point up, or Z, okay? Now, this combination Kx, Ky, this is a B to G times A to G gives me a B1G reduced presentation. However, I can also write down other B1G reduced presentations by combining X and Y spins, okay? So I'm just showing you here that this combination also transforms as B1G. And we know from symmetry that two objects that have the same transformation properties have to be simultaneously present. And that's why I mean that now you no longer think of this spin as having a common d-wave or a single spin direction with a d-wave component, but each spin direction has a different d-wave component, okay? And there's a form factor here that we call eta, just because these two components don't have to have the same prefactor, okay? Now, what it does for us is that if I write down now a very simple model for altermagnetic Hamiltonian, I can write this as an order parameter, and I can just do the scalar product of this d vector with the spins. And what you see generically here is when I have a Fermi surface, I have a metal, is that generically, so the Fermi surface splits in two, except along just now a handful of points. These are the pinch points. And overall, they're going to have a spin texture. Unless I'm looking just in one plane, in this case, k is equal 0, there will be other components. And indeed, these are DFT calculations with ruthenium oxide in this paper. They show that the moment you turn on spin-orbit coupling, you also get X component of the spin away from k is equal 0. Now, you may say, okay, but that's good, but how do I understand that from a real space perspective? Especially because, let's take manganese difluoride. I can just look at the table of the magnetic Wyckoff positions, and I see that the spins in the manganese atoms have to be just collinear, pointing along Z, for that magnetic space group. Even in the fluorides, they have to point along Z. So where is this non-collinearity I'm talking about? Well, this non-collinearity, actually, you can see if you look in the spin density rather than the spin value at the point. So this is a calculation that we did together in collaboration with Turan Birol for DFT calculation, manganese difluoride, showing the spin density for different components in manganese difluoride. You see very nicely this essentially spherically symmetric dipoles for SZ. This comes back to this figure here. But you see now that for SX and SY, you get a non-zero spin density that has several nodes. It actually has properties of a multiple moment, and they're present. Of course, if I look just at the atom, it's 0, but around it, I have a finite spin density. Okay? Now, the other important effect is that if I assume that the spin is pointed out of the plane, but if they point in the plane in this case, now this order parameter here transforms as the EG reduced presentation, which is the same as a ferromagnetic moment. And that means that if, when I turn on spin-orbit decoupling, my altermagnetic moments are in the plane, at least in this situation, they will induce a ferromagnetic order. Okay? Now, for the same token, that same symmetry that allows ferromagnetic order to exist is also going to allow anomalous Hall effect to be present. It's very important to point out that the anomalous Hall is actually not being determined by the magnetization, but is just enabled by the same symmetries that enable a finite magnetization. In fact, as shown by Libor back already in 2020 and his collaborators, that they will have a very large, let's call incipient anomalous Hall effect just from the altermagnetic band structure. Okay. There are other interesting effects. So you can do this classification for any group, any reduced presentation. It turns out that sometimes some spin components will acquire different angular momentum form factors. So the case that actually is relevant for chromium timonide and manganese telluride is that these are G-wave altermagnets. But when you turn on spin-orbit coupling, especially for chromium timonide, where the moment points out of the plane, the in-plane moments now acquire a D-wave form factor. That is the only thing present at k is equal 0, for example. Okay? Now let me talk a little bit more about how the effect of the spin-orbit coupling will impact the nodes of the spin splitting. So without spin-orbit coupling, spin up and spin down, you get proportional to the D-wave form factor, which vanishes actually along two planes. So you have nodal planes, and that's a generic property of altermagnets, the existence of nodal planes of spin splitting. Now, when you turn on spin-orbit coupling, as I mentioned, now you have this D vector, and every element of the vector needs to vanish. And this actually happens for 3 lines. So you reduce the nodal planes to nodal lines. Okay? But what is interesting and important to notice, and this is not particular to this example, is that these nodal lines, they actually are pinned to high symmetry directions by the mirror symmetries of the crystal, okay? And in this regard, if you do an analysis of nodal lines with respect to just the global symmetry properties, they are topologically trivial. However, they are still protected by the crystalline symmetries. Okay, so these are crystalline protected nodal lines. And in this case that I'm showing you, there are two mirror planes protecting. That's why they are pinned to be along this direction. Okay. Now, what say? Okay, well, sure, you have nodal lines that are symmetry protected, but why should I care? Well, you should care because it will matter when I perturb my system. And let's consider the most common perturbation, which is applying a magnetic field. If the field is applied and I still keep one of these mirrors, it means that the nodal lines that are sitting on this mirror plane will not be gapped immediately. Okay? So in this example, I applied a magnetic field along the z direction. Okay? You can interpret this as a displacement of my d vector. And what you find here is that the nodal lines, they still have one set of nodal lines. And instead of being actual vertical or straight lines, they're going to be parabola. Okay? In fact, you can show this exactly playing with this model that the moment you start applying a magnetic field, these nodal lines, they detach from these high symmetry directions, but they're still present. And that's because they still have one mirror to protect them. Now, as I start increasing the value of the magnetic field, these nodal lines, they start collapsing, and there's going to be a critical value of the field where they vanish, okay? But what this means is that there is a nodal to nodeless transition that is topological in the sense that you need to collapse a nodal line, okay? And this only happens, of course, if I apply the field along specific direction, but it shows a stability of the nodal lines of an altermagnet on the presence of a magnetic field because precisely of these symmetries. And I just wanted to point out that, as you can see, I apply a field out of the plane, you see that I broke tetragonal symmetry. And that's, and as you can see, because I only have nodal lines along these two quadrants, and this is nothing but the piezomagnetism. That is another property of altermagnets. How much more time do I have, Asunya?
5 minutes.
Okay. So for the rest of my talk, I want to talk about another effect, which happens when you consider the spin-orbit coupling, which is the existence of Chern bands and via nodal lines. So let me go back to the model, to that simple Lieb lattice model that I discussed earlier. It's when you have the anisotropic hopping along the next nearest neighbor directions, and that Kondo kind of coupling between local moments and itinerant moments. And as I mentioned, right, you have two energy scales. One is the spin splitting, that is proportional to the hopping anisotropy, and one is the splitting between these two copies of the nodal lines, if you wish, along the diagonals, which is proportional to the product of the Hund's coupling and the size of the magnetic moment. I'm going to call this the exchange energy scale, okay? Now, I have presented them here very well separated, but there's an interesting question of what happens when these energy scales are now comparable, okay? And what you immediately see is that now there's going to be an additional crossing, which is this one here, okay? So let's try to see what this means. So here I label the bands. The color blue or red indicates whether it's spin up or spin down, and the plus or minus indicates the two sublattices, okay? So you see now that I have actually two different kinds of crossings. I have the nodal lines that I mentioned before, which are crossings of bands with the opposite spin, but same sublattice. But now I see the existence of another crossing between bands of the same spin, but opposite sublattice. Okay? Now, what is the origin of this crossing? Well, in this particular case, you can actually show that it comes from a higher symmetry constraint that exists on the endpoint. This is just the Lieb lattice, and the Lieb lattice has a quadratic band touching at the endpoint. Okay? And it turns out that when you turn on an altermagnetic order, this quadratic band touching is split into two Dirac points. And these two Dirac points, you see they move in different directions, and they have different spins, if you wish, right? So it matches the symmetries of the altermagnetic order parameter, because it's spin up goes in one direction, spin down goes in the other one, okay? And I'm showing this systematically how it happens, right? I start with non-spin split band, so I have the size of the magnetic moment is 0. Now I turn it on, I slowly start increasing it, there is a crossing, and you see that above a certain critical crossings, the Dirac points meet at the Y or X point and are removed, right? So again, the Dirac point is not guaranteed to exist, but if it exists, it is stable against small perturbations, okay? And again, this goes back to some analysis that agrees with the analysis done by Kai Sun, Eduardo Frodkin, and Steve Kivelson back in 2009 in this paper, okay? Now, what happens now when I turn on spin orbit coupling? Well, when I turn on spin orbit coupling, what's going to happen is that now it depends on the direction of the moments. Let's first consider that the moments are out of the plane. Now you see you gap the Dirac point, but what happens is that I still preserve a horizontal mirror plane, so I get turn bands that are actually mirror turn bands because they are protected by this mirror symmetry, right? And if depending on the parameters of the system, I get an actual turn insulator, magnetic turn insulator. Now, as you can see, depending on the amplitude of the moment or on the value of this exchange interaction, I may actually go from a mirror turn insulator to a trivial insulator just by changing the size of the moments, okay? Now, if the moments are in the plane, then I don't have any turn bands because I break these horizontal mirror planes. I actually get topological trivial bands. I do still get some crossings, and as you can see, there's one here and another one here that are related to the existence of this original node. But again, now I don't get any non-trivial topology of the bands. You see that I consider here two different directions for the magnetic moments if they're in the plane or along the main axis, or if they're along the diagonals. You see that they mix with a ferromagnetic component, and essentially you have either like an effective ferromagnetic or canted magnetic configuration. Just to finish, two very important points before I finish. One is that I showed you an example, but this is not a fine-tuned example. Actually, this crossing of same spin bands are generic to altermagnets. They have been observed in chromium timonide, and the fate depends actually on the symmetries. And we did the same analysis for a rutile model, right, where the anisotropy comes from the third nearest neighbors. And in that case, what you find is that along the k equals pi plane, where you had the nodes, they actually are lifted, but you still have these vial nodal loops in the presence of spin orbit coupling that are actually connected to a Dirac point that exists at the Z here. Okay? So again, this is a generic property, not just for the system. All right, so I'm done. I want to leave you with my conclusions. My main point is, that altermagnets, which you already heard many times in this meeting, is that it actually encompasses a broad range of systems, has relevance for spintronics, but also correlated systems, topological matter. I wanted to mention the fact while the classification is is done without spin orbit coupling, once we include it, it doesn't negate the effects. It actually enriches sometimes the effects by enabling some topological properties, some of them that I showed here. I'll be happy to answer your questions. Thank you.
Okay, sounds good. Yeah. Thank you, Rafael.
Thank you very much. Thanks for the invitation again.
Thank you. Good to see you.
Good to see you too.
Next, we have Professor Rosier Valente. I hope I said your
Yes,
name.
that's all fine. I'm here.
She's going to talk about the fate of altermagnetism in ruthenium oxide.
So first of all, thank you very much for the invitation. It's a pleasure to be here, even if it's only online. And Suyang told me I should talk more about the topic that is a little bit controversial. So that's the topic I'm going to talk about. In fact, what happens with the altermagnetism in ruthenium dioxide. This is a work that we have been doing together with Igor, also with Andre Smolianiuk, who is in the Technical University in Vienna, and my PhD student, Laura Garcia-Gasui. I don't have a photo from her, but she, in fact, has been doing a lot of calculations that I will present. And we have been working together with our experimental collaborators at the University of Würzburg, PSI in Switzerland, as well as ICES in UK. So as we have seen in these nice talks previous to me, one of the materials that in fact has been discussed a lot as a prototypical material, so it's a metal that can bear altermagnetism, is ruthenium dioxide. It has a rutile structure. It crystallizes in the space group P42 mm, so it's tetragonal. The point group is 4 mm. So it's a beautiful example of having here the indeed the manifestation of altermagnetism at a certain critical temperature. So now if we go back in history, this material, in fact, is a material that it's known from a long way back. So there are reports from the 30s talking about this material. And what I'm showing here first is thermodynamic measurements that were done already in the 80s and even before that. And if we look at heat capacity, for instance, what we observed is that in all this range of temperatures, there is no phase transition that it is manifestly happening. So there is no discontinuity in the specific heat. And here on the right, what I'm showing is in fact the specific heat over temperature as a function of T squared at low temperatures. And again, it shows here in comparison to uranium dioxide, it shows the system as there was no phase transition up to very low temperatures. If we look at susceptibility, which has been measured many times, and here I'm showing, for instance, the measurements from these groups, the line that we should be looking at is the susceptibility for this straight line, that is ruthenium dioxide. And again, in a very large range of temperature, it looks rather constant. So it's indicating the system seems to be a Pauli paramagnet. The same if we look at the resistivity. So the resistivity seems to show a very metallic behavior. So in fact, typical of a Pauli paramagnet. So these thermodynamical measurements and transport measurements and susceptibility measurements seem to indicate that ruthenium dioxide, in fact, doesn't order. However, there are also other experiments, more recent experiments. For instance, these measurements by considering the ruthenium L2 absorption H in resonant X-ray scattering, where basically by analyzing the polarization and azimuthal angle dependence of the magnetic Bragg peaks, they could deduce that ruthenium dioxide indeed orders in an altermagnetic fashion. So here is the ordering, which would be to have this altermagnetism. So on sublattice A along the Z direction, it goes parallel to the Z, and then the sublattice B, it's anti-parallel. And the way they were, in fact, suggesting the presence of this magnetic order is, if you will look here, for instance, at the intensity as a function of the angle of the different polarizations, analyzing this intensity peak, they were deducing that the ruthenium was having a magnetic moment that would show ordering below 300 Kelvin, and the magnetic moment rather small, so 0.05 mu Bohr. So this was one of these experiments that were sort of indicating that indeed ruthenium dioxide orders in an altermagnetic fashion. Oops. Also, neutron data from the Oak Ridge group from 2017 They also suggest their observations that there is this altermagnetic order happening in ruthenium dioxide at these temperatures. So what I'm showing here is, for instance, the X-ray diffraction data. So in fact, I should say that the scattering direction, the resonant reflection, the wave vector to look at if one wants to observe this altermagnetic order is the 100 reflection. And the reason for that is because if the magnetic ordering is along the z direction and we have the two ruthenium sublattices, which basically are anti-parallel, they sum up. So what we are going to expect is a scattering along the perpendicular direction, which is the 100. And that's why both experiments concentrated on this wave vector. So in fact, when we look at the neutron diffraction data, what we see is that the X-ray data don't show any peak and intensity at this 100 wave vector. However, in the neutron diffraction data, and these are the non-polarized neutron diffraction data, there is the presence of these two wave vectors that, again, this is compatible with having altermagnetic ordering. And this is the temperature dependence of this neutron diffraction, as well as the susceptibility, where they seem to observe something happening at this 300 Kelvin. And in fact, the order of the magnetic, so the size of the magnetic moment that they deduce in these experiments is between 0.05 mu Bohr in the case of the unpolarized neutrons, up to 0.23, but no, sorry, I think this was for the polarized neutrons and this for the unpolarized neutrons. However, there is a discussion in this work whether they have some structural distortions, so whether they can distinguish this ordering to structural distortions, and this is what I will comment in a moment. So indeed, as we can see, there seems to be a controversy between different types of experiments. So maybe the last experiment I would like to mention is anomalous Hall effect by this group, where they seem to find also in ruthenium dioxide a sizable anomalous Hall effect. And if you deduce from these measurements the magnetic moment, in fact, is much larger than the magnetic moment that was deduced for the previous two experiments that I was showing. So the question is, what is, in fact, what is happening with the altermagnetism in ruthenium dioxide? It seems to be fragile in the sense that some experiments are showing manifestations of it, others don't. Do we have here a sample dependency? So the question that we pose together with Igor and Andrew and Laura is, why don't we look now at the microscopics? What does microscopic tell us? How far can we go by doing a microscopic analysis of the magnetism in ruthenium dioxide? And
Rosie,
the first,
can I ask a quick question? For
yes,
the
please, you
previous
can.
slide?
Yes.
For the previous slide. So here, should I understand the anomalous Hall effect as happens at finite magnetic field because it crosses zero, right?
It crosses zero, yes, and you see that you are at 300. So the suggestion of the other measurements is that you would have this phase transition at about 300 Kelvin. So when you go below 300 Kelvin is when you start to have this signal. And
but
that's
this is not the regular Hall effect.
That's not the regular Hall effect. Yeah.
How do they know that?
That's a very good question. But I think that Libo, you are here, right? Libo, you are one of the co-authors of this work.
Yes. So
Libo, tell us.
So first of all, these are potentially doped thin films.
Yeah, we will come to the doping.
And the assumption was that the z-axis is along the c-axis. So
yes.
When you put it there, you do not expect any anomalous Hall effect. But when you put it into magnetic field, there is luckily in rutile structure Jauschinsky-Murray interaction, which couples the null vector to the magnetic field. In magnetic field, it starts to rotate. It's something what is little known, but there are nice papers from Soviet literature from 70s. And you can one-to-one recalculate how the null vector can rotate, and that should then generate anomalous Hall effect consistent with this. But it's not as simple as in some other materials, which Helena will show, and I don't want to talk about it much longer because it's Roser's talk.
No, it's fine, Libor, but it was just to clarify this, the fact that here you need this Jałudziński-Moria coupling to see the effect.
Nice to see you, Roser, by the way.
Yeah, nice to see you.
Since we started interrupting, just one short comments. First, the kink that you saw on the previous slide is not real. That comes from the insusceptibility. Yeah, they did measurements in two different setups, so they never claimed that there is a. It's basically two different measurements.
I'll come back. I'll come back to that, Igor.
The other thing is that about
wait a second. I will give the talk.
Right.
Okay. Say whatever you want to say.
Yeah. No, I wanted to say that there's this. I don't fully agree with these old Russian papers that he's referring to. In my personal opinion, that Jałudziński-Moria will not do that, but that's something that needs to be clarified.
Yeah, this is something. Okay, fine.
Yeah,
thank you for all the comments to these experiments. Just to show you that there is a lot of controversy with these experiments, and this is where I want now to see where does this controversy come from, and whether we can give a solution to this controversy. And a way to maybe look into that is, let's go to the microscopics. So the first calculation that in fact they are useful calculations at the level that if you want to have something which is materially specific and gives you information about the electronic structure and the magnetism, is basically to do a density functional theory calculation. And this is what we did with Igor and Andrea and Laura. So basically what I'm showing here is a total energy calculation. So when you do a density functional theory by choosing now, the functional that we're choosing is GGA plus U. We need to put, in fact, this Hubbard interaction U if we want to describe better the magnetism in ruthenium dioxide. And since this is a variational calculation, then we always can compare the energies of different states. And what I'm showing here is on the left, this is in fact the data that are red correspond to total energy calculations, and the data that are blue correspond to which is the magnetic moment of ruthenium. So now the calculations were done in the following way, starting at U equals 0, and then ramping up this U and see what happens to the magnetic moment of ruthenium. As you can see, if we go now from the left to the right, by putting larger and larger U's, the energy goes down, but the magnetic moment of ruthenium remains 0. So the system doesn't magnetize even if one goes to very large U effective, which is U onside U minus Hund couplings. Now, the other type of calculation is to start at very large U, so to really bias the system into a magnetic solution, which would be now here, these values of U, where in fact the magnetic moments that the ruthenium get acquired, it's very large, it's minus 0.5, much larger than what the experiments that claim to see altermagnetism seem to observe. And as you can observe, the energy at these very large U values of this magnetic solution is indeed the lowest one. So you would say in this region, in this region, we, I'm going the other way around. We indeed find an altimagnetic ordering. However, if you go now to a smaller U's, this solution very fast is in fact unfavorable, and the favored solution is the one with no magnetism. So now one could say, okay, so one observes this altomagnetic order in the calculations. However, these values of U effective, this 1.5, is extremely large for ruthenium, for the transitional metal ion. So we have done, for instance, constrained RPA calculations for the case of MOT insulators with ruthenium. And the largest value that one obtains for this U effective is of the order of 1 electron volt. Here we are talking about ruthenium dioxide, which is the metal. So that means the screening effects will be important. So we should be talking about, in fact, U effective values that are in this region here, which would correspond to the solution of no magnetic ordering. Moreover, if we look now at, so furthermore, maybe what I should say that in this solution here, these very large U values in this altermagnetic solution, indeed DFT predicts also the which is the direction of the magnetic moments, which is the one also claimed in the experiments, which would correspond to have the magnetic anisotropy along the z-axis, or basically the magnetic moments oriented along the z-axis. So, so as I was mentioning, this U effect is very unrealistic. And moreover, if we look at the density of states, which is also an indication of where do we have the instabilities, when we look at the Fermi level, what we observe is that at the Fermi level, there is a strong depletion of density of states. So that means that you don't expect, in fact, an instability towards magnetism. But what is interesting about this density of state, which here is just shown orbitally resolved, is that one has a very large density of states in the occupied region, which of course could be reached, for instance, by doping. So if we put now some doping in ruthenium dioxide. So then in fact, what we did is indeed to investigate what happens with the possible appearance of this altermagnetism if we start doping the system. So by changing the number of electrons, and then this is what I'm showing here is, in fact, the magnetic moment of ruthenium that is acquired by just doping. This is now whole doping the system, and as a function of these U effectives, of this U effective value. And what you can observe that as soon as I have whole doping, in the regions of realistic U effective for ruthenium dioxide, that we start indeed getting solutions where the ruthenium is magnetic. So that doping induces some magnetism in ruthenium. So yes.
Sorry, how it translates these numbers in terms of electrons per unit cell?
Okay, so so 56 corresponds to the pristine ruthenium dioxide. And now by going into down is basically where you have 2%, 3% or 4%. In fact, here is about 10% of basically of whole doping that you would introduce. So if you think in terms of having ruthenium vacancies, for instance, in your system, it would correspond to about having 10% of ruthenium vacancies.
Okay.
If you want to translate that. So this is what this calculation suggested, that we may be having an issue with the samples. And we know, in fact, I didn't put now here the references. There are some references that are indeed indicating that they have some ruthenium vacancies in the samples. So what we next did is then, together with our collaborators in the different big places where they do neutron scattering experiments at PSI, as well as mu-SR experiments at ICES. So basically, they had high quality, both single crystals and also, let me just take that here, and thin films. And basically, they did a very careful analysis of what neutron diffraction is giving to these crystals. So in fact, these ruthenium dioxide crystals are, I think, a millimeter large, and they are quite pure, so quite pristine. And what I'm showing here is the intensity of this reflection that I was mentioning to you. So this is you would expect, as I was mentioning, the strongest magnetic scattering if we have this configuration along this reflection. And here what I'm showing is, so basically what the neutron scattering measurements show is that there are some scattering angles where this reflection, even if they do observations, so they have the statistical average of long time, so 10 hours, basically they don't see any changes. So they don't see any effect in this. They don't see effect seen at this reflection. However, if they go to very low angles, what they observe is indeed some signal, but only within a few minutes. And it seems, and this is for the neutron scatterers are the experts on that, is that this is not typical of a observation of a Bragg peak. And it has in fact a name. This is called the Renninger effect, which is indicating that what one is observing here, or what one is having, is effects of multiple scattering. So indeed, they did a very careful analysis of all these different angles. So, and basically what they conclude is that they are not observing Q equals 0 magnetic ordering. And let's say the upper bound that they have of magnetic moments would be a 0011 mu Bohr. So, and in fact, they reanalyzed the data in the other paper, and basically that's that could be one of the sources of the observation of this magnetic ordering in this in the previous neutron diffraction data, that it could come from this multiple scattering. So this is, in fact, one measurement that I wanted to mention. The second measurement done by, in fact, in the group of Simon Morza, and these were measurements done at, as far as I think it was at ICES. So these experiments, again, so that's mu-SR. So the idea, as you know very well, with mu-SR, you implant polarized muons, and then they decay with a certain lifetime of the order of 2.2 microseconds. And then they emit a positron, which is preferentially in the direction of the polarization, if you have a polarization in your system. And now then what you measure is the asymmetry in the decay, which should be proportional to this polarization. And here what I'm showing is this asymmetry in two measurements, a zero field measurement, and then applying a magnetic field of the order of 5 milliteslas. And what they observe is that there is, here is shown for as a function of time for different temperatures, and they don't observe any relaxation or depolarization. There is no missing asymmetry, both in the case of zero field and in the case of a finite field, where then you have the Larmor precession, and they don't see any asymmetry going away from the typical Larmor precession. So again, the conclusion is that they don't observe magnetism. So there is no magnetism in these rather pure samples. Both, they did these measurements in single crystals as well as in thin films. So the conclusion is that if you have a rather pure sample, so pristine ruthenium dioxide is such a good metal that the magnetism is not there. Well, we also try to, in order to get no possible explanation that, for instance, you could have some fortuitous or some special coincidence that it could be that the muons maybe are not seeing the magnetism, we also help with calculations of with DFT plus mu calculations, where basically one can identify first by doing this DFT calculation which would be the stopping sides of the muons. So the idea is basically to calculate the electrostatic potential, and where you are going to expect this muon to stop is where you have the largest negative potential. We just expected is going to be far away from your ruthenium. So this is these regions shown here in blue. So first of all, we know where these expect these muons to stop. And then what Laura also did is to calculate, in fact, whether there could be some possible diffusion. So Laura and Igor were doing these calculations, whether the muons maybe could possibly diffuse, because then again, your signals could be indeed influenced by possible diffusion. And in fact, what I'm showing here is the 3 positions of where this muon can sit. And this is now the calculation of the energy along, so by just considering the position of this muon along this line here. And as you can see, that there is these very well defined wells in energy, so that this is telling us that we are not going to expect effects of diffusion. So these mu-SR experiments, again, are indicating that there is no detectable ruthenium magnetic moments. So this was the conclusion from these studies, that ruthenium dioxide is very metallic. But now we saw in the calculations I was showing to you that doping the system in some way, either you have ruthenium vacancies or any other type of doping, you could induce, in fact, altermagnetic order. And this is, in fact, results by Andriy and Igor, where they, in fact, there is this material where there was recently, in fact, this work where they were claiming that they were finding an emergent and now zero field, so not defined, but zero field anomalous Hall effect in this material. So in ruthenium oxide doped with chromium. And when one looks at this, in fact, at this formula, so the system that they seem to have, we have here 20% of chromium, which would correspond to 0.4 holes doping. So according to the calculations that we had, we would expect altermagnetic ordering. And these are, in fact, BCA calculations done by Andriy, where indeed at this, so if you have this doping and you look at the energies, you would expect at this doping the winning energy, so the magnetic ordering that is more stable is an altermagnetic ordering. So this would fit in principle with these experiments that we can discuss later on, whether the experiments have some issues, but this would fit. However, the virtual crystal approximation is not always a good approximation. So what do you do in the virtual crystal approximation? So basically you start with your unit cell for your ruthenium dioxide in this case. And what you do then is artificially change ruthenium by a mixture of ruthenium and chromium, so by an artificial atom, and you redo the calculation. So this would mean, if you do this type of calculation, that you are assuming that you have a completely uniform doping of the system. So what Andriy did is, well, this is a very rough approximation, we should do supercell calculations, and this is what he did. And if you do supercell calculations, so then you really take very large supercells and you insert this 20% chromium, the reality is very different. So what happens then is that chromium likes to cluster and ruthenium doesn't acquire any magnetic moment. So what happens is that what it's formed in the crystal, and this is what is shown in this nice simulation, is that the chromiums cluster and they form ferromagnetic clusters. And what these measurements are probably measuring here is the clustering of chromium dioxide. And because it's ferromagnetic, they will get, in fact, an anomalous signal. So they will get a whole signal. So this is telling us that ruthenium dioxide is not the best system probably to look for altermagnetism. We have seen that there are other materials that are really beautiful, show this altermagnetic ordering and all these features that we have been seeing in the previous talks. But ruthenium dioxide is not a good one because what all these calculations as well as mu-SR, neutron scattering, and thermodynamic measurements show is that it is rather sample dependent, the fact that where you find altermagnetism or not. And even in the chrome dope case, this type of doping builds these chromium dioxide ferromagnetic clusters, and you don't see these altermagnetic ordering. So with that, I come to my end. We have been doing also more in on the lines of what Rafael was presenting. Of course, altermagnetism is really a beautiful concept to think of, and we were very much interested in whether we can induce with, in fact, with correlations, altermagnetic type of order, whether we have phase transitions between insulator and metal type of altermagnets. And this is the recent work we have done with Francesco Ferrari, my postdoc, on the Shaftesbury-Sutherland model. This is for another time. So with that, I conclude now today with ruthenium dioxide. And thank you very much for your attention. And I'm happy to answer questions. Igor is also here, so we will answer all possible questions. So
okay, so our last
sharing,
speaker is Professor Helena Ryklova. I hope I did
yes,
okay.
You made it.
I'm still sharing or no?
Yes,
yes, now.
She's going to tell us about investigating magnetothermal transport in altermagnet. Please, Helena.
Okay, so let me share the second screen. And I make it full screen. So you do see my full screen, right? Yeah.
Yes.
Okay, excellent. So thanks again for invitation to this wonderful workshop. And I will cover really the experiments here. So I will try to skip all the introduction, which was wonderfully done by the speakers before me. And I will focus only on some magnetothermal transport in certain altermagnets. And also I was trying to on fly edit the talk, what I was hearing. So I also added there 1 or 2 slides about the ruthenium dioxide. And then I will also move to the mangan telluride, which was discussed, and the mangan 5 silicon 3, which was also mentioned. So yes, we already heard like that spintronic with compensated materials and generally with antiferromagnets is an attractive field. So there are advantages also from the application perspective, right? So like this absence of the stray field or the faster frequency of switching. And also that the choice of materials is much broader, that we have insulators, metals, semiconductors readily available when we are in the family of compensated magnets. And now, before I go to the experiments on altermagnets, let me just recap a bit the spintronic effects in antiferromagnets, what we know about them, where we have real experiments, real experimental data. So anomalous Hall and Nernst effect, it's already very, very well known that it can be present in many of these systems after the pioneering work from Professor Nakatsui and Professor Felser. It was observed in many other materials. So the anomalous Hall and Nernst effect, let's say, is checked. And then tunneling anisotropic magnetoresistance, which is, let's say, from the application perspective, the key effect, which is very interesting. And here, there was tunneling anisotropic magnetoresistance, basically with one magnetic layer observed, let's say, 2012, some time ago. We did some experiments and it was possible. And then only last year, we also there was also two works from 2 groups independently, which indeed show that one can have tunneling magnetoresistance with 2 antiferromagnets separated by an insulating layer. And going to the gigantic magnetoresistance, where the insulator is replaced by some conductive spacer. Here there is a theory, beautiful theory work, but experimentally we lack the evidence, and this might be related to the absence of samples which sufficiently perfect quality of the interfaces, and also the fact that it would require, in this system we would require like a coherent spin current going through the spacer, which is not trivial. Let's say having these material systems which were used before. I will just maybe change it to the laser pointer. So, and now when we look at this brief recap, which most of you probably know, we see already that what I was talking, where we have really some experimental evidence, are non-collinear antiferromagnets. So when we now look what we know about collinear antiferromagnets, so we already had it nicely summarized by Libor also, that the anomalous Hall effect in this conventional collinear antiferromagnets is simply forbidden because of having the TT symmetry. And then the tunneling magnetoresistance, it's kind of absent. There could be some tunneling anisotropic magnetoresistance relying again on the anisotropic magnetoresistance, which is present in the collinear antiferromagnets, or on this iron rhodium, which has very particular properties with some help of phase transition between ferromagnetic and antiferromagnetic. There was experimentally measured some tunneling anisotropic magnetoresistance in that case, but again it's a rather fragile effect. And the gigantic magnetoresistance is the same story. It's a discussed, but for example, in this nice work, it's again summarized that such an effect is possible only in the materials which exhibit some spin splitting, which brings us to the family of materials which we discussed today here, and these are the altermagnets. And here we see that the anomalous Hall and Nernst effect is predicted, measured. This will be the center part of the rest of my talk. However, also the effects which are more important from the application and more important for driving really the altermagnetism business is the tunneling anisotropic magnetoresistance and giant magnetoresistance, which was predicted and in altermagnets, and should be much more robust than in the collinear antiferromagnets. But as I mentioned, I will now focus on this anomalous Hall and Nernst effects. And I will just, so that we are on the same page, summarize what I mean. So anomalous Hall effect is the well-known phenomena where we generate voltage perpendicular to the current and a magnetic order vector. And the anomalous Nernst effect is the thermoelectric counterpart, where the voltage is generated perpendicular to the applied thermal gradient. And we expect to observe saturation at certain magnetic field, and ideally also the presence of the effect at zero magnetic field, what I call then spontaneous anomalous or Nernst effect. And why to study it? So in particular, the anomalous Nernst effect is relatively difficult to measure. So why to put all the effort and study it? So the anomalous Nernst effect might be very, very elegant way to actually harvest the waste heat, as shown and discussed a lot by, for example, the Uchida group, because of its favorable and simple design, that we need only basically one layer of a material. One can imagine that such a layer of material can be wrapped around any source of heat, such a pipe or anything, and then the geometry, this perpendicular geometry would be immediately fulfilled, and the voltage would be generated in the direction perpendicular to the heat gradient. And when we have well designed magnetic material, the magnetic order vector. And second, maybe still more scientific reason to study the anomalous Nernst effect is that, as we shown, it can also enable a magnetic microscopy tool where the thermal gradient can be generated not only globally, but also locally by, for example, a laser spot. And the laser spot can scan over a sample surface, again generating locally the favorable geometry for the Nernst effect, because the thermal gradient is in, let's say, out of plane direction. The magnetic order vector is in some in-plane direction, and when it's perpendicular, the voltage detection, we can pick up voltage, and by that we can scan locally the properties, the magnetic properties on a sample. So it's good to know also about anomalous Hall and Nernst effects in the altermagnets, but also what as an experimentalist we like is that the experiments are relatively simple. We don't need any complicated heterostructures, we don't have interfaces which always complicate the story, and we can simply use one single layer of materials and study the effect. So let's start by the anomalous Hall effect. So everything was already said. I think that it requires the time reversal symmetry breaking in the electronic bands. And historically, it was considered only to be present in materials with a net moment, in ferromagnets. However, I think it's already very well established that anomalous Hall effect does not arise from the net magnetic moment, and the intrinsic contribution can be present in the non-collinear antiferromagnets. And in 2020, as Libor and colleagues shown, that it can be present also in class of collinear magnets compensated, which have a particular crystal symmetry, nowadays called altermagnets. And so how do they differ from this cartoon, which I showed already before, and which was already now set by a couple of speakers before me, that we now consider also here again, when we do the time reversal by the arrow, we can by the translation by a half unit cell, recover the original picture, therefore the TT is a symmetry. However, here we consider also these non-magnetic cages, and by doing the reversal of the spin by half unit cell translation, we do not recover the original picture, and therefore the symmetry is broken and allows for the anomalous Hall effect. This brings us to the question if the anomalous Hall effect is a good tool to identify altermagnets. First, I should say that it's indeed an indirect tool. So compared to some RPES or some direct technique to visualize the electronic bands, it's an indirect tool. On the other hand, we have a couple of features or hints how to check for the anomalous Hall effect originating from altermagnetism, and one of them is, for example, that in the ferromagnets, as it was also mentioned today already, this is not ferromagnet, but in ferromagnets, simply the anomalous Hall effect, we can always find the perpendicular direction, somehow rotate our contacts and find that anomalous Hall effect will be there. So anomalous Hall effect cannot simply disappear. However, in the altermagnets, it's not allowed for every orientation of the null vector. Therefore, we expect the effect to be highly anisotropic, and this is something which I will come back later. And the second point is that anomalous Hall effect in ferromagnets is observed in polycrystalline samples, polycrystalline materials. However, here in the case of altermagnets, we rely on the crystal, we rely on the non-magnetic environment, and therefore the crystalline quality also should, in this logic, play a role for the presence or absence of the anomalous Hall effect. So let me then go to the work, which I will summarize. So here I just show an example of the growing family of experimental altermagnetic evidence, let's say, and I will talk about only the anomalous Hall and anomalous Nernst effect, but there is many more experiments which I think are nicely complementing the work which I talk about. So here I now put the three concrete material systems. So I didn't plan to talk much about the metallic ruthenium dioxide exactly because it's a to some way controversial system, but I will now try to add a little bit comments to what was said, and after it I will move to the semiconducting mangan telluride and this thin films of the mangan 5 silicon 3, where the anomalous Hall effect, let's say, is also experimentally for us much easier to measure because it's spontaneous and present in zero magnetic field. So the ruthenium dioxide, as Roser nicely summarized, was used, or now is used, like when we take the model cartoon as a model system. However, in the physical or the realistic realization of the films, we are not sure about if these experiments are to be trusted. And this was also something which we kind of wanted to test on the samples, actually from also Simon Moser from Würzburg. So the samples which Simon grows are indeed of very, very high quality. Here are some TM data. We check that they are indeed metallic. We check that they are having really no net moment, so that it's not in this doped regime where they are inducing some small ferromagnetic moment, like with this chromium doping. And we wanted to look at or basically reproduce the work of the Feng group, and inspired by the theory work of Libor and others, we knew that the null vector in this model, when it's along 001, then we do not expect any anomalous Hall effect. However, if there is any projection to the 001 plane, then there should be appearance of the anomalous Hall effect. And unfortunately, in the samples which we got, we assumed that the orientation of the null vector is exactly along this 001 direction. So then experimentally one needs to count them away from this 001 direction, and one has to put the any projection of the null vector to the plane, to the 001 plane. And here this probably controversial thing. However, I have to say that this old Soviet papers, they were also supported by experimental data. Maybe we should actually also try to repeat it, this observation which they made, which they claim that when one applies magnetic field perpendicular to the null vector, that counterintuitively with what we would expect in some picture which we are used to think about antiferromagnets, then counterintuitively to this expectation, there is starting the sort of counting of the null vector towards the field 110 field, and it develops small net moment, but in the same time, this projection to the 001 plane also then allows for the altermagnetic anomalous Hall effect. So from here, we see that first, what we expect is a combination of the ordinary Hall effect in the signal, then some small contribution from the net moment which we develop, but it should be dominated by the strong altermagnetic contribution, and it should be very highly anisotropic. Yeah. And so here, let me summarize the slide, also the work which Feng and others did, and which Roser also had on her slide. They prepared, building on the fact that it should be so highly anisotropic, they prepared ruthenium dioxide samples grown with different orientation or differently oriented substrates. And what they say is now, okay, so this scenario which I just described should be happening in this case of the sample. This is where this old Soviet paper claims that when we have the null vector here, it starts to count towards the 110 direction. And this should be not present here and here in this 001 and 100 oriented samples. And then they measure until 50 Tesla, and they see that indeed the only change or change in the slope they observed in the sample, where they expect the counting of the L vector towards the 110 direction, therefore development of the moment or the projection of the null vector, which allows for the anomalous Hall effect. And here they do not observe this this feature. We try to reproduce this data. So we took the sample where they saw an effect. This is the 110 oriented, and we went up to 50 Tesla and even higher to 68 Tesla. And we indeed saw that the values were similar to the one which were measured by the Feng and others. And also we saw that it's indeed starting to saturate approximately where one would expect that the null vector is counted towards the edge to this reorientation field. And we just check again, like more for experimentalists, that indeed it's the slope is same for the pulsed and DC field, because for this high magnetic fields one needs to use pulse field. So we were just wondering if there are not some artifacts. And we also checked the temperature dependency, and again we got a surprisingly good agreement with the Feng paper. So here, just this is like what I want to leave here, that we observed the same what the group of Feng observed. We kind of observed that the anomalous Hall conductivity here is like 1500 Siemens centimeter. So yes, so pretty large, cannot be explained by the small net moment. So it, again, I would say that in the thin films, yes, it's a adventure how this will develop, if the magnetic order is there or not. So then this will only time show. Good. So let me move to the less controversial system, let's say, which is one of our beloved materials, mangan telluride. Mangan telluride is we have thin films and also bulk, which is a semiconducting material, and here the manganese atoms are surrounded by these tellurium cages, and with this kind of rotation and translation symmetry, it fulfills the criteria of the altermagnetism. And indeed, already some time ago, the calculation showed that the splitting is present in the outside of the high symmetry directions, and the anomalous Hall effect is allowed. And importantly here, because the spins are pointing not along the C direction as in the chromium antimony, but in the AB plane, they are also, the anomalous Hall effect is also allowed in the zero magnetic field. The band structure in that case was confirmed by the RPES experiments by Juraj Krempanský and co-workers, the beautiful work which Libor also mentioned. And so let me go directly for the transport measurements. So here what we do, we pattern Hall bars from the mangan telluride thin films, and we measure longitudinal and transversal response. In the longitudinal response, we see standard magnetoresistance or anisotropic magnetoresistance. I will then mention it a little bit in more details. But what is maybe more interesting is the transversal signal. And here on the transversal signal, it's a sweep of the magnetic field and already subtracted linear slope. So already only the data after subtracting of the ordinary Hall effect. But what is important here, that also in the zero magnetic field, we observe a clear opening of the loop. We see spontaneous signal. We see also a signal being saturated approximately around the spin flip field as we expect. And here, just like adding a cartoon, so here we see that the altermagnetic properties here, the presence of the tellurium cages of the non-magnetic atoms also makes the difference, let's say, between this state and this state, right? So when we would have as we were used to think about collinear antiferromagnets a couple of years ago. So having such a cartoon, we would break our head and think like, okay, so why these two states have different signal, why they are having different anomalous Hall effect when just by shifting them by a unit cell, half unit cell is the same. So here I just schematically highlight again that although they have no net magnetic moment, they don't need to have any net magnetic moment. The presence of this non-magnetic environment is enough to allow for the difference in the anomalous Hall effect. And the spontaneous signal indeed disappears at higher temperatures. The critical temperature is around room temperature. So here it's closing a bit below the critical temperature, but simply it behaves as one would expect. So this is the anomalous Hall effect, and I mentioned also that the longitudinal data contain also some interesting information, and this is about the anisotropic magnetoresistance, which we knew very well that it contains some of the non-crystalline contribution, which has like this cosine square symmetry. However, also the crystalline contribution, which has the six-fold symmetry. This is what we can nicely see here, which indeed copies the crystalline properties. In the conventional picture, if we would think about some ferromagnet, in this kind of crystalline contributions, we would not expect in the transversal signal, in the transversal contacts simply. Some people would call it planar Hall effect, but let's just call it transversal signal here. And here we see that in our case, the transversal response is not only the cosine-like contribution, which we would expect, but also the threefold symmetry here. And this threefold symmetry again shows that it's yet another evidence that the anomalous Hall effect, which we observe, is indeed of the altermagnetic origin, and it's also present in this angular dependent magnetotransport. So here I just put also one slide, just to know that the mangan telluride is a beautiful system, but there are also open questions. And one of them is, for example, that we now also look in the bulk crystals, not only in films, as also some other groups. I know, for example, this group, but there is also a group in US which has beautiful data on the bulk mangan telluride crystals. And indeed, also in the bulk crystals, we observe a spontaneous anomalous Hall effect. This is all fine, but similar to us and also the group of the team of Klučik and al. They also observe that the effect is present, but you see that the sign, for example, of the effect is opposite to the sign of in the thin films. And also that the coercivity is varied significantly between the samples. I know that some of the samples don't even show the anomalous Hall effect. So this kind of inconsistency between different samples grown by different methods, this is also something which we try to understand now. And yes, it's a work in preparation. So the last material which I want to mention is the mangan 5 silicon 3. And this material is actually beautiful because it's just a mangan and silicon, very simple elements, and they are grown on silicon in our case. So, but let me start by introducing that in the bulk, this material is known to have multiple magnetic phase transition, and from the paramagnetic state it goes to the collinear phase where the spins are arranged collinearly in such a fashion, and in the low temperature phase the spins are getting some non-collinear ordering, some non-collinear fashion, and in the very low temperature even more manganese are getting ordered, and it's getting really complicated. So for us now, let's say the medium temperature phase, the collinear phase, is the interesting one, and so we try to grow it in the form of thin films. And in our case, we grew it on the silicon 111. And this was because the silicon 111, when we grow it on this orientation of the silicon, we actually stabilize hexagonal structure. And I will explain why is it important. But before that, I just want to show an experimental evidence for the hexagonal stabilization in the full temperature range. So here it's a temperature dependent structural data, temperature dependence X-ray, and we see that in the bulk. Bulk mangan 5 silicon 3, the material undergoes a structural transition together with the magnetic transition. So in the C parameter that we see the transition very clearly, and also in the AB we see it very clearly. And now with our films, we grow it on the silicon 111. We have the AB lattice parameters fixed by the silicon lattice, and the C is the perpendicular to the film plane. So the C is free to undergo the some transition at the transition temperature. However, not the AB in our films, which is fixed by the silicon substrate, and it remains in the hexagonal unit cell. The X-ray always measures the samples as a bulk, as a kind of average technique, and we also did X-ray, transition electron microscopy to look locally and to just confirm that our hexagonal lattice is consistent with the localized, but on a couple of spots localized picture, which we did by TM. So we see that here the mangan silicon indeed forms this structure which we assumed by having the silicon 111. One interesting thing is that by growing it on the on this silicon films, we stabilize this hexagonal unit cell. And unlike the bulk, which has this transition from the hexagonal to tetragonal and the monoclinic, we are now having it hexagonal in the full temperature range. So there is no reason for the doubling of the magnetic unit cell, and we maintain the magnetic unit cell same in these two different rectangles, right? When I visualize it like that. And then we can do the same exercise as I was doing before, that we flip the spin. We would, let's say, flip the color here, and by shifting it in that direction, in the case of bulk, we would indeed get the same picture. So we would have something which does not allow the anomalous Hall effect. However, here, because of the change of the cell, because change of the underlying lattice, we are now having the copy of the same structure here, and therefore by switching the color here, I cannot find any operation how I would basically recover the original picture. So the TT symmetry is broken, and indeed, based on the calculation from the team from Mainz, the anomalous Hall effect is allowed. Here, just a small cartoon that naturally we draw it here, that this is like how the arrows are pointing, but this is also supported by DFT calculations that indeed this checkerboard ordering is the ground state. So having this experimentally checked and theoretically supported, we were patterning the Hall bars. And one interesting thing is that the strain not only that stabilizes the hexagonal unit cell in the full temperature range, but it also shifts actually the Nel temperature, that it's strain shifting the Nel temperature, which afterwards we found that it's not so obscure, that it's happening in other materials as well. So in our case, the Nel temperature is approximately 240 Kelvin, and it's paramagnetic above. Here in this temperature range, it's a collinear system, and here in the low temperature regime, it's non-collinear, and we are not so focused on the low temperature phase, which is rather complicated. We always check the magnetometry. So magnetometry of compensated magnets is notoriously difficult, especially when there is a substrate. which we have to somehow subtract. But to the best of our resolution and capabilities, we always try to give upper boundary to the magnetic moment, which we observe. And here in this case, we give upper boundary of 10 millibor magneton per manganese. And importantly, we see no basically change in the full studied temperature range, let's say in the low temperature or the room temperature, which is already above the magnetic phase transition. This is in a clear contrast to the transport data. So here I'm showing already the anomalous Hall effect as a function of the out-of-plane magnetic field. And we see that in the full temperature range, where the sample is magnetically ordered, we observe a robust anomalous Hall effect, which is spontaneous, present in zero magnetic field, and the effect disappears above this 240 Kelvin, and at room temperature where it's paramagnetic. So this was, let's say, work done already some time ago. So just to summarize, so we checked the hexagonal unit cell, we checked the vanishing magnetization, we checked that the anomalous Hall effect provides an evidence of the spontaneous time orbital symmetry breaking, and we have this confirmed theoretically that this crystal structure and magnetic structure allows for the altermagnetism. So therefore, it's a strong evidence that the spontaneous anomalous Hall effect in that case originates from altermagnetism. And as I mentioned, that it's not a direct proof. So there are also some other additional hints why we think that it's indeed of an altermagnetic origin. And I mentioned the role of crystallinity, right? So that in the polycrystalline film, we should lose this advantage of the sublattice making us allow us for the anomalous Hall effect. And so indeed we had samples with varying quality, polycrystalline, some mixed and epitaxial films. And here we, in the polycrystalline sample, observe only some, this is really raw data as we measure them. And we indeed observe no spontaneous signal, only some probably misalignment, some sort of magnitude resistance coming from the misalignment of the contacts. In the mixed samples of the mixed quality, we start to see some sort of anomalous Hall effect opening, and only in the samples which are really very high quality, we see the nice anomalous Hall effect. This is indeed the raw data as they come out from the measurement system. And we also asked, can we then correlate it somehow with the crystal quality? We had a set of measured samples. All of them show some form of the anomalous Hall effect. All of them have approximately a similar critical temperature. And we also try to compare the quality by looking at the XRD data, by comparing the content of the ordered mangan 5 silicon 3 with some sort of impurities which are unfortunately sometimes present there. And by this ratio of the crystal phase of the mangan 5 and the impurities which are the mangan silicon, we could correlate the anomalous Hall resistivity at let's say 150K. We didn't see anything in the polycrystalline sample, and then it was to some extent scaling. And it was in contrast to the squid data, where we measured all of these samples by the magnetometry. But yes, there is no correlation. Whatever we measure there, it's not correlated with the XRD. So this was the role of the crystalline quality. And second thing, which I mentioned already, that the anomalous Hall effect can be used to detect the altermagnetism, is the highly anisotropic character of the magnetotransport. And in case of the anomalous Hall effect, when we talk about ferromagnets, we typically assume or expect to see some cosine-like behavior of the standard permalloy or iron or some ferromagnetic material. However, in the altermagnetic, we know that in certain orientations of the Nel vector, the anomalous Hall effect is simply forbidden. So there should be some plateaus or some regions where the effect is simply not there. And indeed, this is what we observe here. So let me show these data. So here we have certain orientations where the anomalous Hall effect is absent, and then certain regions where suddenly like the anomalous Hall effect appears, and then it still fulfills this sort of cosine-like symmetry, but with this highly anisotropic character. And here in the gray points, we also show the squid data, which are in no way correlated with this anomalous Hall data, with this anisotropy of the anomalous Hall data. And we again here in this case combine the samples of the high crystalline quality with the samples of the poor crystalline quality, and our assumption confirms that the highly anisotropic transport or highly anisotropic anomalous Hall effect is indeed present only in the ordered crystal, and in this poor quality samples, we are sort of towards the something which we would expect from the anomalous Hall effect in ferromagnet cosine-like dependency.
Helena, can I ask a question?
Yes.
When
Yes.
you rotate the angle, is it satisfied that at all angle where your current and your Hall voltage and your magnetic field are perpendicular to each other, or
Yeah, it's the orientation of the current and the magnetic order vector, you know. So this is not the magnetic field, which because you have to assume how the magnetic field, what the magnetic field does to the spins, right?
okay?
And then what it does to the spins, then this matters for the for the voltage which you measure on the anomalous Hall effect. It's not the magnetic field, or the magnetic field matters only for the ordinary part, right? The cosine-like part. This we sort of, yes, this is there, but then the rest depends on the orientation of the magnetic order vector. So
I see. So I have to understand how the magnetic field influence the magnetic order.
Exactly. And in the mangan 5 silicon 3, we are in a relatively lucky scenario that we can even manipulate the spins with the external magnetic field. This is magnetic field of 4 Tesla, right? So it's not a small field. So it should, if we put iron or anything, the magnetization of iron would be fully following the magnetic field. And then indeed you would think about it like magnetic field cross product with the current is my, then indeed you would think about it like magnetic field and current. But here, yes, here it's not so like simple thing.
I see.
But still we have shown in the sweeps that we can control the magnetization or the anti-thermal or altermagnetization, or however we want to call it, by the external magnetic field, that we can control the spins by the external magnetic field.
Okay.
Do I still have time to talk about the last part, or we are
I
out
think
of
we
time?
should just wrap up this part.
Wrap up. Okay. This part or the full talk? I will.
Just wrap up the full talk after this part.
Okay. So then let me just skip to the. I will skip the Nernst effect then, and just go then to the summary. So I will just show one last slide.
Sure.
So we also looked at not only the anomalous Hall effect, but also at the anomalous Nernst effect. And what we observed was that indeed in this material, although it's composed from very lightweight elements, and it's a metallic system, so all these things which would normally act against a measurable and significant anomalous Nernst effect, we could observe clear spontaneous anomalous Nernst effect. And when I now show here just like a one table of comparing different materials, antiferromagnets, ferromagnets, and this, let's say the first Altermagnet, we can see that when we look at the magnitude of the anomalous Nernst effect, this compound is already pretty decent compared to the others, because when we look this symbol size should somehow illustrate the lightness or how heavy the compound is, and the large values are indeed from compounds which are based from uranium or ytterbium, the nice work where very large Nernst effect was observed. And then there is the cobalt, mangan, gallium, where it's a ferromagnetic Wilson metal. But after that, already our compound has comparable values to the others, so which makes us relatively optimistic that the altermagnets are also beneficial for the anomalous Nernst effect and anomalous Nernst optimization. So let me bring to the conclusion, so that the spintronics with antiferromagnets or compensated magnets generally is useful, and the anomalous Nernst effect is not only good for the heat harvesting, but could be also interesting for the microscopy. And then we start by the anomalous Hall effect, and I discussed three material systems where we observed the effect. And also we observed it on the first collinear compensated magnet, this mangan 5 silicon 3. So thank you for your attention.
Thank you, Helena, and thank all the speakers, and thank you all for being here. We have an amazing turnout. Hi, Liver. Thank you. And yeah, hope you enjoy the workshop. And I think this will be posted online at some point.